ফুল স্ক্রিন টাচ আসছে, কোনটা আসছে? না না মিউট করা আছে, বন্ধ করা আছে না? হ্যাঁ তাই নাকি? আচ্ছা বন্ধ করে থাকলেও আসছে। ও তাই কালকে বলেছিলে, দেখি। ও
ஞாபகம் வச்சுக்கோ. அப்படியே அவங்க இந்த டைம் பண்ணியே ஆகணும்.
So good morning to all participants. How you feel about yesterday's day one sessions? रुको Okay. Good morning from India. Good morning, Professor
Morning.
Ghosh.
Morning.
It's pleasure to see you for the first time
Nice.
through this Google Meet.
Yes. Sorry, I couldn't attend yesterday because I was driving back to my home. So,
So you
and
you are you are living in Wilmington.
Wilmington, North Carolina. Yeah. It's close to 11 now. So,
Very good.
yeah, I haven't used Google Meet for long. So, okay. So, this is the button for present now. Okay.
This arrow button.
The arrow button. Okay. Okay.
So are you from West Bengal? But your microphone is off.
For that, still trying to familiarize myself with this thing. But yes, I'm from Kolkata, West Bengal, but precisely from Howrah, I would say.
Okay, okay.
Just give me 1 second. I'm trying to. Yeah.
And how long you been there?
And you mean in the US or
In the
in
US.
this close to? Well, it's. I came here in 2006, so
That was
it's
so.
been 14, maybe 16.
Uh,
So, do you know by any chance, Professor Subroto Chakraborty, uh,
Dibrugarh University.
Dibrugarh? Yeah. Actually, I met him in a conference, and we worked in a couple of projects. In
Uh,
fact, I'm going to present a paper which Subroto Da is one of these. Uh,
Collaborator.
yeah.
We'll start after exactly 4 minutes, 3 minutes, like
Okay.
5:30. This you may check whether it is present or not. This present now button.
Okay. Let me check. And prior to that, I guess I need to open my PDF document, the presentation, maybe. Let me check
Ha
quickly.
ha. Uh,
So it is open now. Let me, okay, present now. Enter screen.
uh,
No, not.
you, you can if that window is open, then you can do it a window. Otherwise, uh, you enter screen.
Okay, let me, a window. Oh, okay. I think that's fair enough.
Uh,
Is that now visible?
yes, it is visible. Now make it full screen.
Okay. Ignore. Where is the,
Go to this view option. View option of the PDF.
oh, okay. That's, okay. Okay, view and make it
Full
full
screen.
screen.
Wow. Yeah, it comes very nicely.
Okay. Thanks.
Just move one or two pages. Just move one or two pages so that it may confirm. Okay, fine.
Okay, great. Okay. Thank you.
Uh, so our participants are watching through YouTube also.
Oh, so this is live on YouTube as well?
Ha ha ha.
Oh, wow. Okay.
For your information, we have received 400 registered participants all over the globe, especially from Algeria, Sweden, Iran, Pakistan, some
Oh,
other countries also,
oh, wow.
Palestine. And yesterday, up to 3:30 Indian
Uh,
time, there was invited talks. After that, there was a parallel session. So there were eight parallel sessions yesterday, and today there will be seven parallel sessions.
Oh, that's great. Okay.
Uh,
Yeah, I wish I could attend to quite a few of them, but it's the time difference.
time
That's
difference. That is why we have given you the early morning because it is night at your time.
yes.
What is the
Exactly.
time over there?
Right now it's 11 in the night.
Oh, 11.
So all these talks will be available on the YouTube link. Like if
Ah, it will be
okay.
available. So, shall we start?
Well, I'm ready. Just let me know. Yeah.
So, good morning to all, one and all present over here, and as well as in the YouTube sessions. Welcome to this day two of our international conference on emerging trends in pure and applied mathematics. Today, in the day two, we have one invited speaker with us, Professor Indranil Ghosh, who is associate professor of statistics in the Department of Mathematics and Statistics in the University of North Carolina, Wilmington, USA. And let me know something more about him. He is an elected member of the International Statistical Institute and also the current chair of the Risk Analysis section of the American Statistical Association. His research area includes, but not limited to, univariate, bivariate, multivariate, and matrix-variate characterization of probability models, classical and Bayesian inference, financial risk modeling, survival data analysis, hidden truncation models, measures of divergence in the assessment of compatibility and near compatibility of probability distribution. He has published over more than 65 articles with a citation of in total 800, and today he will deliver a talk with the title A Bivariate Poisson Conditionals Distribution Properties and Application. So with this, I welcome Professor Ghosh to deliver his talk. Over to you, sir.
Thank you, Professor Devnath. And first of all, I would like to offer my sincere thanks to the members of the organizing committee for, for preparing or coming up with this wonderful conference virtually with this pandemic still on. I think this is a great opportunity for virtually to meet researchers from all around the world. And I'm very much honored and thank you for this invitation. And I hope that with my talk, there will be some amount of interest. The audience will have some interest and they might have some questions, which I'll be happy to answer after my talk. And even in between my talk, if there are any questions, please feel free to just let me know. All right, so today I'm going to talk about this is a joint work with two of my collaborators. One is Professor Philip J. Marques, Philip from University of Nova Lisboa, Portugal, and the other person is Professor Subroto Chakraborty from the Dibrugarh University in Assam. This work has been published in Journal of Applied Statistics in 2020, and this talks about a bivariate Poisson conditional distribution with some structural properties and application. And let me just come up with a brief outline of my talk. So, bivariate, my talk will center around this bivariate Poisson conditionals distribution, copula-based simulation study. Then I will talk about some of the applications of paired count data exhibiting negative correlation and followed by some concluding remarks. So one of the major motivation for us was that in the continuous domain, like almost on a daily basis, a new univariate continuous, absolutely continuous probability model or even bivariate would come up. And there are several journals, they publish these papers, but on the contrary, there has not been that much extent the work on the discrete area. I mean, one of the reason could be it's not very nice analytically tractable form of the discrete distribution, even with a bivariate univariate domain. For example, binomial distribution, the cumulative distribution function for the binomial is not in nice form. It involves incomplete beta function. The only tractable form that we would have is for geometric probability model. So even on the univariate domain, the existing form of discrete probability models are quite, at times, even the normalizing constant is cumbersome, but they have a lot of application. Now, if we just move from univariate to bivariate, well, there are not many. I mean, there are distributions. There is a book, Bivariate Discrete Distributions, by Balakrishnan and his co-author, but those forms are not easy to comprehend, as well as in terms of interpretation. Now, with today's modern computing, very strong either packages in R, statistical software, or in MATLAB, or in Mathematica, or Python, or SAS, I mean, in terms of application, it may not be very difficult, but still, there are still some open issues. And that was one of the reasons that we thought of, well, let's explore this distribution. And the other major motivation was that there are, at least to the best of our knowledge, there are not many distributions in the bivariate domain for discrete data that account for negative correlation. There are quite a few that can appropriately explain or model the positive correlated scenarios, but not many in negative, if the two variables are negatively correlated. Now, this, I want to make sure that a couple of things. Number one is that we didn't derive a new distribution. This distribution has been developed independently by Ovechkov back in 1969, if I'm not missing the exact year. And then it was by Arnold, Casillo, and Sarabia in their book, Conditional Specification of Statistical Models. That came up in 1999. So what we did was that in that book, Arnold and his co-author, they talked about some of the structural properties, but there was not much discussion about the proof for the negative correlation as well as an application. So those were the major motivating factors that sort of helped us to continue with this project. So, and with this bivariate discrete Poisson distribution, I mean, there are quite a few, in particular in the literature. And it has enjoyed a good amount of attention for a couple of decades. So basically, we are focusing on a paired count data exhibiting correlation and possibly representing over or under dispersion. Now, surprisingly enough, I mean, Poisson distribution, if one is quite accustomed with the terminology and statistical properties of Poisson distribution, if X follows a Poisson distribution with parameter lambda, then the mean and the variance is exactly equal to lambda. So usually Poisson distribution cannot be applied for models with whenever you have a data set for which the expected value is bigger than the variance or expected value is less than the variance. So, but for this bivariate discrete distribution, which we do not call a bivariate Poisson, but the conditionals are in the Poisson family. So I'm going to go in a moment about the structural properties, but what happens is that instead of the joint distribution X and Y, we have Y given X for each possible values of X is a Poisson with the model parameter depending on the conditioning variable, as well as X given Y also follows Poisson. And from that, one could get the joint form. Now, in terms of application, it has a lot of application in like marketing, number of purchases of different products, epidemiology, accident analysis. In fact, Poisson distribution is typically used for modeling rare events like, let's say, earthquake or any others, let's sort of natural calamities. So there is a lot of use of this particular distribution in the univariate domain in terms of accident analysis. It is also used in medical research, in sports, and other domain that might affect our daily life. Now, in this case, we are focusing on a correlated bivariate Poisson distribution, and in particular with a negative correlation. Now, the usual one, sorry, the references are somehow properly, but it is, I have my references. It is basically reference 2 and 4 in the reference list. The most celebrated form of a bivariate Poisson distribution that starts with 3 independent Poisson with parameter lambda sub I. Then it's a convolution, y1 as sum of x1 and x3, and y2 is x2 and x3. And in that case, if you start with this 3 independent Poisson and create a bivariate distribution with that sort of formation, then the joint distribution, joint discrete probability model would look like this. And it is, there are a lot of books and papers in which this form has been utilized. It's quite a popular model. And it is, one can find this details about this probability model bivariate in Balakrishnan book on bivariate discrete distribution and other papers as well. Now, one of the major limitation of this particular form of bivariate distribution is that it can only be applicable to data set where there exists a positive dependent structure between the two. Moreover, since the marginal distributions are Poisson, that is y1 would be Poisson distribution with parameter lambda 1 plus lambda 3, and y2 would be another Poisson with parameter lambda 2 plus lambda 3. So it cannot be used to model over or under dispersion because of the reason I mentioned earlier. So as a remedy, there are different ways one can construct a bivariate probability model. The one that we are concerned with is the conditional specification, and the reference is the Arnold, Casillo, and Sarabia book. And the references, several other pertinent references are given as well in that book. Now, in this approach, actually, they started with 2 conditionals, which are of Poisson type, and the parameters depending on the conditioning variable. And then they came up with the most general form of bivariate Poisson conditional. So the beauty of this model is that the associated marginal distributions for X and Y, they can address the scenario of over and under dispersion under certain parametric restrictions. Now, interestingly enough, the marginals are not Poisson. So the only conditionals are in Poisson family, but not the marginals, as well as the bivariate distribution is sort of Poisson type, but we cannot say exactly a bivariate Poisson model in its traditional sense. So here it is. So X given Y, Poisson with this particular form, and lambda 1, lambda 2, these are the 2 model parameters that are specifically belongs to X and Y respectively. But lambda 3 is the dependence parameter. So lambda 3 is sort of coupling both X and Y. And if you set lambda 3 equals to 1, then X and Y are independent. And based on the Arnold and his co-authored book, I mean, it's given in Theorem 4.1 on page 76, the joint PMF is given in that form. Now, where X is from 0 to infinity, Y is 0 to infinity, and this K, which depends on lambda 1, lambda 2, lambda 3, is the normalizing constant. So in all our analysis, we have utilized this equation 1 as our bivariate model. And this is what we call bivariate, in short, BPCD, bivariate Poisson conditional distributions with three parameters, lambda 1, lambda 2, and lambda 3. And as I was referring earlier, this joint PMF in equation 1 is also known as Obertkopf distribution. It has also independently derived by another researcher, which I have in my list of references. Now, in terms of properties, well, the marginals are Poisson type, but not exactly. So the marginals are of this form, and what this particular result, in fact, is identified by my co-author Subroto Chakraborty, that for fixed lambda 3, the joint distribution or the joint PMF, to be more precise, if you rotate the role of lambda 1 and lambda 2 for fixed lambda 3, it doesn't change. I mean, the PMF exactly appears to be exactly same. So if lambda 1, lambda 2 equals to lambda, then these two probabilities are exactly the same, meaning that we might get symmetric shapes. And that has also been established by some of the joint PMF graphs that we have mentioned in the paper. Those graphs were obtained by Mathematica, and my other co-author, Philip, has done work on that. And if anyone is interested, I mean, the reference is there, and I'll be more than happy to share our paper. Well, of course, there are a lot of open questions on that, which I will come towards the end. So here are some of the useful summaries: the expected value of X, the expected value of Y. And this is very important. The covariance between X and Y is of this particular form. And theorem 1 is, it is not that we have established, but the proof was not given in the book. So this is quite interesting and important contribution as far as our paper goes, is that we were able to show that if XY follows this bivariate Poisson conditional type distribution, then the covariance between X and Y is less than 0. And likewise, we can, at least in a closed form expression, we can provide the joint factorial moments. And from factorial moments, one can obtain central moments of higher order, and that will help us to get moment-based measures of skewness and kurtosis. And those details are mentioned in the paper, but for the sake of this presentation, those are excluded. And again, of course, one can get the joint probability generating function, and the joint moment generating function is just a simple transformation. Now, theorem 4 talks about the properties of X and Y in terms of their distribution. Like if X, Y follows this bivariate distribution as in equation 1, then X plus Y will also have Poisson, provided lambda 3 equals to 1. And our result on B is like a standard sort of undergrad statistics class type exercise, that for if lambda 3 equals to 1 and X plus Y is a Poisson, then the conditional distribution of X given the sum of is a binomial with that particular choice of the probability of success. And of course, because we started with X given Y Poisson and Y given X as Poisson, one can simply equate X and Y corresponding to the conditional expectation to get the linear regression of X and Y and the regression, or just in general, regression of Y on X. So in that perspective, theorem 4 has some utilities. And theorem 5 talks about stochastic ordering. Now, stochastic ordering, it has some application. And precisely, as far as I know, is that a lot of this stochastic ordering has to do in financial risk modeling. So here we mention the following, and the proof is in the paper. I have all these properties, except for a couple of them, I have derived them, mentioned them in the paper. Now, what happens that if lambda 1 is bigger than lambda 2, then for the dependence parameter, which is between 0 to 1, x is stochastically larger than y. And if lambda 1 is less than lambda 2, then y is stochastically larger than x. And if anyone having any question on stochastically larger properties, is that it's just a definition that if you say x is stochastically larger than y, then for any x which is in the support set of let's say x and y, probability that capital X bigger than small x is that probability is bigger than probability y bigger than small x. So that's what it is. And theorem 6 also talks about the utility of this particular model, that the marginals exhibit over dispersion. So in modeling real life data where you have the presence of negative correlation and also marginally component wise, if they exhibit over dispersion, then this BPCT model could be a reasonable good candidate to explain that particular data set. Now, in terms of estimation, well, in the paper, we considered the classical approach and the maximum likelihood estimation. The standard procedure says, let's say you have paired random sample of size m, x1, y1, x2, y2, xm, ym. Then we can create the log likelihood function. And from that, the usual MLEs will be obtained by taking partial derivative of the log likelihood function with respect to lambda 1, lambda 2, and lambda 3 and setting them to equal to 0. Now, here comes the trouble that, well, at the time when we were developing this, we didn't came up with any of the R packages. That's one of our future plan to come up with a specific R package, because none of the existing packages could have solved our problem. And also in Mathematica, when we tried independently, Philip and myself, we had some trouble with the convergence issue, because the MLEs we were getting, they were very sensitive to us if we change the one parameter to the other. And if for example, lambda 3, the dependence parameter is always between 0 to 1. But when we simulate from this distribution or even trying to fit to a real data, there were some cases where the values of lambda came as negative, and in some cases well above 1. So that is not correct. So we had to drop the idea of going through the straightforward MLE approach. And then Philip came up with the idea of using the copula. And what we had to do an extensive literature review, and we find that it's not the first time we are thinking. There are some instances in the literature that utilizes, in particular for bivariate Poisson distribution, the use of copula-based estimation. So we sort of mimic that idea. So what we did, this part was effectively done by Philip. So if you have any question, I can share that with my co-author, Philip, in this particular aspect. So a random sample of 10,000 samples are generated from two copulas. And in one phrase, a copula is a bivariate or bivariate distribution with the uniforms, with the marginals are in uniform. So it is very useful tool. It has a lot of application in financial sector. And it helps us a lot because we do not have to know the complicated or awkward normalizing constant for a bivariate or multivariate distribution. We can simply equate the marginal CDF and we can consider the associate copula. And it is much easier for us not only to discuss the usual correlation coefficient, but there are other types of dependence measure that can be well studied with the help of copula. And to know more about this copula and their properties, I would suggest there is a book by Roger B. Nelson on the copula. So, and in fact, the PDFs are available on Google, I suppose. So you can have a look at that. So we consider two specific type of copula. One is in the family, and the other one is the extreme type copula, so that we get a comprehensive view on how effective is this approach. So we considered a bivariate normal copula with correlation coefficient rho and Morgenstern FGM copula with dependence parameter alpha. And what we did is that in the copula, we just utilized two component copula, two marginal Poisson distributions with parameters M1 and M2. The purpose was to understand how this bivariate distribution described in the PMF in equation 1 may be used to model bivariate data arising from a bivariate normal or FGM copulas with Poisson marginals. Now, one might argue that does this truly reflect the form as if coming from the equation 1 PMF? Well, it is close to that. That's our conjecture. We will not say that it is absolutely perfect. It is not. But in the absence of non-tractable likelihood function and non-availability of any such packages, we were forced to consider this approach. Now, the simulation from a copula-based distribution is usually straightforward when the marginals are continuous. But here, it is discrete. So, and if it's a mixture of discrete and continuous, a more careful approach is required. And I have those references. Sorry about that. Some of these references came up with a question mark. But I'm going to mention what are those references at the end. So here is the form of the copula, because if you equate those U1 and U2 are as if coming from an uniform distribution, because there is a standard result that the CDF follows a uniform under certain conditions. So in this case, you match U1 with the Poisson marginal with M1 and U2 with another Poisson with M2, and then you couple them with this theta is the dependence parameter, which in the bivariate normal case is the rho, and the FGM copula, it is the alpha. Now, to generate this distribution, sample from this distribution, we have to first sample vector U1, U2, and then take the usual inverse approach. And in one of these references, the author present an example of a method that may be used to simulate discrete dependent Poisson variables using a specific type of copula. And in the reference, we have mentioned that. And in fact, one can get also or simulate distributions from multivariate domain as well, or multivariate count data. And for the simulation, Mathematica software was utilized to implement this methodology. Now, in the simulation study for the bivariate copula, the correlation parameter was floated around negative 0.9 to 0.2. And for the FGM copula, the dependence parameter alpha was floated around from in the same domain from negative 0.9 to 0.2. And the MLEs of lambda 1, lambda 2, and lambda 3 were obtained using the procedure as described in the reference. Now, as expected, which we will see in the table upcoming, that the fit of the BPCD distribution to the data generated from bivariate normal and FGM copulas, we considered the chi-square goodness of fit test. And this was also mentioned in the section 3 of the same reference. Now, here is the thing that when we have a small negative correlation, then it can be characterized by a BPCD distribution, which in alias, as if coming from this B bivariate normal or FGM copula. Now, when the negative correlation is stronger, that is smaller than negative 0.2, the null hypothesis, which states that the population distribution is BPCD is rejected, which is quite expected. So as we see here is that from this table, these were the estimates of lambda 1, lambda 2, and lambda 3. Noticeably, we'll see that when the true correlation from the sample was negative 0.82, it was capturing to some extent. Even up to this point, when the correlation was negative, the model, the bivariate Poisson conditional distribution with the help of this BN and FGM copula, so it was, or it is capturing, not to that extent, but these are quite good in a way. But when it is positive, it's not as expected because the model is only can capture negative correlation. And this is with binormal, bivariate normal copula with M15 and M210. So here also similar feature is being obtained, that when the, for example, true sample correlation coefficient is negative 0.49, our bivariate Poisson conditional probability model is capturing the amount is negative 0.41. So it's pretty much close. And this is with the FGM copula, similar pattern. I mean, this is almost perfectly capturing, but as this is quite good, in fact. The true sample is correlation coefficient is negative 0.26, while the model is negative 0.25. And we are, as if we are taking the help of FGM copula with the dependence parameter negative 0.9, but it is closely something that is coming from a bivariate Poisson conditional distribution. And we are sort of mimicking the idea in that reference, which says how to deal with this bivariate discrete probability models simulating using a copula. So these are some of the results. And now coming to this real data application, well, this data set is taken from the English Premier Football League, which is available in that particular reference. It is also available in GitHub for our bloggers. So we have got 5 seasons, and each season giving us 380 pairs of counts, namely the goals scored in each game in the form full-time home team goal and full-time away team goal. And it came up with the negative correlation. I mean, that's from the sample data. And we conjecture at this point that the bivariate Poisson conditional distribution proposed in this paper will have a reasonably good fit. And in the next table, we provide a descriptive summary of the data for each of the 5 seasons respectively. And as expected, pairwise negative correlation is observed. So here it is for the 2014-15 home team, away team, the correlation is negative 0.3, for 15-16 is negative 0.02, and so on. For 2018-19, it's a negative 0.17. So it's a negative correlation. Now, what we did is that by the same approach, instead of simulating the data, now we have the data itself, we fit with this bivariate Poisson conditional distribution. And what we observe that it is pretty much, it's quite good in terms of fitting or capturing the true dependence structure for all these season, pretty much. So that was one of the, well, we didn't find that many applications. It was a little bit hard to come up with a data set that might well be represented with this bivariate Poisson conditional distribution, at least for this particular model. But we are pretty sure that there might be some other data set for which this model might find a good place. So in summary, the statistical analysis of bivariate count data, well, it's challenging because of the lack of parametric class of distribution supporting a rich enough correlation structure. So in our paper, we studied a particular distribution where the conditionals are in Poisson form, and that accounts for negative correlation. But in terms of when we apply, there are some, there are still some questions. So another way could be in terms of estimation and statistical inference could be considering Bayesian approach in which the parameters lambda 1, lambda 2, and lambda 3, one might come up with a, if it's about conjugate prior, maybe gamma distribution with proper choice of hyperparameters, and some information from the practitioner might be given, and then we can come up with updating those priors appropriately and follow the usual Bayesian approach, full conditional prior approach. Now, the other thing is, if we consider non-informative prior in the Bayesian context, then it is basically the maximum likelihood approach. Now, we are, one thing I must say that we are not claiming that maximum likelihood approach or the classical standard way cannot be done, but it is, with our experience, we didn't find. And even when we tried, we had some issues regarding convergence. So that's the thing. But one may try and come up with creative ways of writing code, and that might work. We don't know. Now, application of this bivariate Poisson distribution as a tool to model bivariate count data is not new in the literature. Like there are several different references, like the Balakrishnan book, the Arnold Casillo Sarabia book, where they have mentioned several other references. But several such earlier proposed model has the drawback of its inability to model data set exhibiting negative correlation. So in this paper, we have explored and studied in details a particular type of bivariate Poisson conditional distribution described in Arnold and his co-authors. And we were also able to establish that under certain parametric conditions or restriction, this model will exhibit negative correlation. In fact, always in the beginning, we are thinking, well, it could be that it might be able to exhibit positive correlation, but it's not, as suggested later on by Arnold. Now, one of the useful and interesting feature of this particular discrete probability model is that it is free from the limitation that the derivation of any structural properties, including its derivation of marginal distributions for X and Y, that involves evaluation of incomplete gamma function. So like for bivariate Poisson distribution that started with 3 independent Poisson, and then you couple them with the convolution, they have the, even for the univariate standard Poisson distribution, the CDF for a Poisson distribution, it does involve incomplete gamma function if someone wants to write it in a closed form. But that will not happen in this case. Now, another aspect would be for us to see how the model can be generalized to the multivariate case. A substantive amount of work is needed in this direction to see the applicability of such models in practice. However, before we can think of extension to multivariate version, we think that it should be motivated from a real world perspective. I mean, from theoretical point of view, well, someone can definitely start, but these days you need to have at least some application of your proposed statistical model. Otherwise, it would be very hard to publish in a standard or good journal. Being said, that's all regarding talk. And here are some of the references. So I've been talking about, let me specifically go about each of these, not each of these, but a couple of these important one. So this is the book I was referring to earlier, Conditional Specification of Statistical Models. And in fact, this gentleman, Arnold, happens to be my thesis advisor. And this is the book that talks about the conditional binomial, Poisson distribution in independently. by Atchison and Ho in 1989. So this is our paper. The details are provided here in the Journal of Applied Statistics. And then this is the book I was referring to. So Balakrishnan, Johnson, and Coates, Discrete Multivariate Distributions. And then this is the other reference I was referring to, like the chi-square goodness of fit statistic for bivariate discrete distributions. And this is a very nice book, by the way, by Kocher Lakota S, and by the same last name with the different first name, bivariate discrete distribution. And then this is the one, Oberchkov, 1963. So that's one thing. And here it is. This is one of the major references that we got some idea on Kopylov models for multivariate discrete response data. And this is the reference that we sort of mimic the idea by Trivedi and Zimmer on a note on identification of bivariate copulas for discrete count data. So we got a lot of help from this reading this particular paper. So that being said, that's all I have for you. Thank you for your attention, and if you have any question, you can ask me at this point of time.
Thank you, Professor Ghosh, for a nice talk. So this floor is now for the discussion with our invited speaker. So any one of you would like to ask anything regarding his talk or related to your research topic also? Professor Ghosh, not directly to involve with your talk, like we are doing also mathematical modeling. In this case, what we do, we take some of the parameters, follow some distribution. Some of the parameters follow some distribution, and suppose if we are cost minimization problem or profit maximization problem, so we take the expectation. So is it a good way to tackle such type of problems, or what are the other ways we can like tackle this type of modeling?
Well, of course, that like you said, that could be an approach. I mean, these are all possibilities. I will not rule out in favor or against of any of these procedure, but we were thinking of from a very simple perspective that, okay, let's say we have a model, and let's say here are the maximum likelihood equations. Let's see if it is not that it cannot be done, but we were sort of surprised that there are some issues in the literature, and many people have indicated that it may not be an easy way to deal with, especially for bivariate discrete probability models. And that's why the copula-based method came up quite popular in a way. Expectation max EM algorithm, well, it will, as you were indicating. So it could be. It could be. I mean, we haven't explored. I mean, that's the thing, but it could be.
Okay. Understood. So any other question? Yesterday one session was on statistics only.
Okay.
Some of the faculties from different universities and colleges, they were participate. Also discussing some algorithms. Mm-hmm. So like in your statistical models, any kind of algorithms are used?
Well, I have used, I mean, for example, I have done work on Bayesian statistical inference. In fact, for standard probability models, usual Bayesian analysis with priors and conjugate priors, non-informative priors, and so on. Even I just did a paper with my advisor on, it's on probability models that do not have even a form of the density. So it's called, and there is a method called approximate Bayesian computation. So there is a particular technique, and even on R, there are some packages. So of course, I have utilized that. Of course, I have to write my own code little bit to deal with the setup, but it is available. So these days, I would say that I will not say it's impossible, yeah, with these supercomputing facilities that these days we have. It's just that for our paper at that time, we didn't explore separately because I guess for conditionals models, I mean, or bivariate distribution coming out of discrete conditionals, there needs to be a separate discussion. We need to explore it. It cannot be done, or we couldn't do in the form of a paper, but maybe a separate paper which one will discuss with all these estimation procedures separately.
So, like different kind of bivariate distributions are newly developed. So, for someone to develop something new bivariate distribution, what are the conditions that that means it should follow so that everyone can
Well,
follow?
of course, first thing first, you have to consider the literature, existing literature, that what are the current trends and what are the methods they are used. There are several different methods, like you can start with three or four independent components and then couple them like ratio or sum or difference. Let's say y1 x1 minus x2 and y2 is x2 minus x3, things like that. Then there are approaches with the just the sum. There are several different other approaches. So I would, for example, I would suggest the book on that multivariate discrete distribution. I do not have on top of my head, but there are certain approaches that are nicely discussed in that book by Johnson, Coates, and Balakrishnan.
Okay, thank you. Like I am also working on inventory modeling that
Okay.
comes under operational research. So I could explore something new from your topics, and it was really a nice topic and nice discussion. Although,
Yeah, I'll be more than happy if you have any question I can
uh,
share or email me.
uh, okay. So thank you once again for being here, and in future also, like uh, we believe that we could possibly come to this place of this Assam. This is a very nice place, actually, Tezpur University, very near to this Kaziranga National Park. Hope you know about this Kaziranga National Park. So,
I have heard of it, and I have a long-standing wish to visit. So
uh, uh,
hopefully,
since your collaborator also from Dibrugarh University, Dibrugarh
yeah.
University is just 4 hour distance from here, or
Oh, okay,
maybe
okay,
less than that, less than that.
okay.
So,
Well, good to thank you. Thank you for the invitation.
uh, good night to you. Thank you.
Thank you. And I'll be watching on YouTube maybe tomorrow morning some of these talks.
Uh,
And
uh, okay,
thank you.
thank you.
Thank you. Bye.
Uh, you may stop this presentation. So our next presentation presenter is Professor Deptani Chakraborty, who is yet to join. So there is a small announcement that there will be a valedictory session in the afternoon 5 o'clock. So all of you please be there. Google Meet link is already shared with you in the schedule. So uh, let us wait for 5 minutes because our next session is from 10:30. So we'll be there. Okay. So just be there for another 5 to 5 minutes. She'll be joining soon. Or if you have any question, you may ask me. There is an announcement. Our next speaker is Professor Devdana Chakraborty, who is yet to join. Our next session will be start from 10:30 a.m. And those who have not filled up this feedback form, I am again sharing with you all. Please fill up it, and all of you be in the military session through this Google Meet link. This link already shared in the schedule. Good morning, Professor Manoj Kumar. The microphone is off.
Yeah, yeah. Hi, good morning. How are you?
Fine. You, sir?
Yeah, I'm fine too. Yes, thank you. So we'll start at 10:30, I think, right?
Yes, sir.
My talk is at 11:45. I know that, but the next talk is at 10:30.
10:30. Professor Devdana Chakraborty, madam, but
Yeah.
he has not joined yet. So
Okay. Anyway,
probably I should mail her again. Good morning, ma'am.
Good morning. Good morning.
Ma'am, shall we start now?
Yeah, yeah, you can start.
Okay. So, welcome to all. In this session, we have with us Professor Devtani Chakraborty, who is a professor in the Department of Mathematics, IIT Kharagpur, also holds the position of Associate Dean CET, and her area of research includes multi-criteria decision analysis, optimization in imprecise and uncertain environment, fuzzy logic, and approximate reasoning in medical imaging. And till now she had guided more than 16 completed and ongoing PhD students, and awarded by Young Scientist Award, Young Scientist Scheme from DHT, nominated member of Indian National Academy of Sciences, Research Associative from CSIR, Research Fellowship from CSIR, Best Paper Award in 2 international journals, and many more. So with this, I welcome Professor Chakraborty to deliver his talk. Over to you, ma'am.
Okay, very good morning to everybody. Hope your conference is going very well. And today is the second day, I feel, and there was a session
Yes, this session is.
before to this talk. Yeah, I have seen. I wanted to join, but somehow I could not manage to join in the inaugural and other sessions. And I have seen the YouTube that connection, and it is very nice. I have seen yesterday. Now, let me share my screen. Is that okay?
Yes, yes, ma'am.
Just to check. Is it visible?
Yes.
You could see my PPT.
Yes, ma'am. Please make it full screen mode.
Yeah, I'll do it. Now it's okay.
Yes, it is okay.
Now, today's talk is on the introduction of fuzzy geometry. Now, we have developed few tools for defining fuzzy geometry, but the quest started when we were analyzing the optimization model, because understanding the optimization model involves a sequential process of obtaining the reasonable solution. Now, through the optimization model, this is our general process is to get the final solution through a black box algorithm. Now, whenever we are defining any optimization model in fuzzy environment, we could see that the optimization models are the feasible space, that is the objective function space even, are not defined properly. So we thought that if the solution space of a fuzzy optimization model, fuzziness occurs whenever there is uncertainty due to the perception of knowledge, due to the inexactness of the representation of information of the optimization model regarding the parameters. There the fuzziness occurs. If we do not know the objective functions, the parameters related to the objective functions, rather the coefficients related to the objective functions as well as the constraints, in an exact way, in a precise way, but this is given in as fuzzy sets, then the fuzziness occurs. But this is the sample model you see here where there is no fuzziness. The constraint, the decision space, CAPEX, now is defined very nicely. The edge of the solution space is precisely defined. But solution space of a fuzzy optimization model is hazy in nature. That's why we started thinking if the boundary of the fuzzy feasible region is hazy in nature, then how to handle it? Then we thought that, if the fuzzy curve is there, instead of this curve, if we have a fuzzy curve, that is a hazy curve is there. And we know any curve is a combination of the points in geometrical sense, and there is a underlying property for defining it. For example, x square is the underlying property. We know all the points over here are having the property like x square or x minus 2 square. All right. But if this is not defined properly, if it is itself hazy in nature, how to handle it? Then we thought to develop fuzzy set theory, where fuzzy geometry, because we thought every point would be the fuzzy point. It's not a general point. Therefore, we started searching the literature. We have seen in the literature the fuzzy geometry has been defined very in a basic way by Buckley and Islami long back. Then we started to thinking the optimization model with those definitions, but there was we could not find any proper theory to explain the fuzziness. So we started doing the two-dimensional analytical fuzzy geometry. Today I thought that I should talk on that only, how our journey started and how we started to think what is a fuzzy point, what is a fuzzy line, how to define those in a closed form, what about fuzzy circle, etc. Now, in doing so, I thought to start my lecture with a multi-objective problem. You see, there is a bi-objective problem where first objective function is minimization square and second objective function is minimization of x minus 2 square, and x is lying between maybe minus 4 and 4. If you just look at the space, for multi-objective problem, for the objective functions there is a trade-off between the objective function, because you see from 0 to 1 the first objective function x square is increasing, but the second objective function is decreasing, even from 1 to 2. From 0 to 2 itself there is a trade-off, but if you just see minus 4 to 0 or 2 to 4, you will see both the objective functions either decreasing together or increasing together. Now, this is the basic idea of a multi-objective. We are looking for the Pareto optimal solutions. We won't get any single optimal solution which can best satisfy both the objective functions together. But this is not really the concern of my lecture today. I am not really going to detail the multi-objective cases, but my discussion is something different from that. Just I will show you that the same problem we are in. You see, instead of taking x square, we have taken fuzzy 1 into x square. Similarly, fuzzy 1 x minus 2 square. How fuzzy 1 would be? Maybe guessing that there is a coefficient for x square is first the value to be from 0 membership values from 0 to 2 at 1. This is maximum, that is. If we consider so, we will see that there will be a case here. You might be seeing a portion of the previous curve I have shown. Only the region that adopted and just looking at that from 0 to 2. Instead of a single line, single curve, we're having now you see it's a now the closed form of the curve has to be defined properly. We have to see the behavior of the curve. We have to see what are the points which will lie on this curve. That cannot be a single. Am I audible to all of you? Hello?
Yes, ma'am.
Yeah. Suddenly I thought that whether I'm audible or not. Okay. And now you see the points on the curves are not really of similar nature. These are having different shapes, we can say. If I ask you what would be the point at 1 where two curves are intersecting, can you say in geometry there is a single point? Not really. We will have a combination of points in the intersecting curve. Now we got how to define a fuzzy point in the next. This is another example from the objective level, but as I said, this is not really my concern to explain. Just I wanted to show you that this is an example where we are looking for the fuzzy Pareto optimal frontier. The same curves as I was explaining here, but here we are having the fuzzy curves. Okay? Now, therefore, we can say that if this decision space is there and if decision problem, then very easy is that the Pareto front. And from the red line is acceptable to us. Then whenever for a this then only we can define. Okay, now the same definition. Why am I next? But I want to mean that whatever we defined before, that was lacking certain logic. Therefore, we started finding. Then Gupta and Ray, Amar, Pham, Lee and Gu, and all these people did something on fuzzy geometry in an explicit way, in a closed form. They were giving the equations of respective fuzzy objects, like for the circles, for the conic sections. Our journey we started. And of see the construction procedure of fuzzy geometry has not been focused. And as you know, in the school level geometry even, whenever we are defining we there was no clear idea about the measures like area, height, width, distance between fuzzy sets. That when these are all been measured. Area of fuzzy circle, that the boundary is fuzzy in nature. How it could be that the area is crisp? Area is precise. It can't. Therefore, these ideas lack in a conformity when reduced to the corresponding classical geometry idea. And in 2009, Professor Jadhae, who is an exponent of fuzzy set theory, he said that the counterpart of a crisp curve C in Euclidean geometry is a fuzzy curve. A fuzzy shape may be formed by a fuzzy transformation of C, where C acts as a prototype for fuzzy shape. If we just draw any geometrical object like fuzzy line, fuzzy circle, fuzzy conic section, we can do it with a spray pen, as if we are using a spray pen and we are drawing it. For example, we have a bloating paper and we are using pen. If we start drawing the line, we will see that the ink will spread unevenly, and the central part would be very dark, and the boundary of that band would be very light, fade to white. Then we have black to white in that band. Jadhae defined fuzzy curve that way. But again, the same question, how to do it? Then we started thinking how a fuzzy point. Barclay Islami defined this way. If I say that there is a point in two-dimensional space, that the coordinate of the point is 1, 3, the fuzzy point could be a region, which would be a collection of points with different membership grade. And the membership grade can be defined with the given equation. But you know, in fuzzy set theory, these members, that is the big question, what would be the membership function? But this refers to the perception of knowledge, perception of information. Now, perception of the individuals, whatever membership function you will think, I will think differently. Anyway, that is not my concern today, how to define the membership function, what is the significance of membership function in fuzzy set theory. But my concern is to explain, you see here, if we consider the membership function this way, then we can say that we are defining one point, that is the fuzzy point, but it is hazy in nature. The central region at 1, 3, it is black and it is faded away from black to white smoothly. Maybe my drawing is not really proper, but think that way, that the black is fading out and it is going to white. Okay, this is a very hazy region. If we look at a far distant point, we will see it very hazily. That is not really precise. Now, mathematically, we can say that there is a mathematical form of it, and this is the mathematical representation of fuzzy point. Everybody will accept, yes, this is the definition. And mathematics people will be happy to see the equation behind it. But how to define this point? If you remember, if you know fuzzy number, may I assume all of you know fuzzy number at least? Yes or no? Do you know fuzzy set theory, any one of you?
Yes, ma'am.
Yes, if you know fuzzy set theory, then if you know fuzzy number, for example, you see my lecture was today at 10:30, but I thought it is around 10:30. That's why I entered little bit before, and I saw the forum is open, I can start my lecture. Therefore, it was not exactly 10:30. Some time before 10:30 is there. I thought it could be even beyond 10:30, but exactly 10:30, I'm sure the forum is empty and I can just get into it. So if I utter the sentence that my lecture is at around 10:30, then this 10:30 is not really a precise number. This is a fuzzy number, which includes the time points before 10:30 and after 10:30. And generally, we are defining with a triangular way for our, it may not be triangular, for our advantage, we are considering it as a triangular, and we say at 10:30 it is maximum, and before to that there is a possibility to enter. There is a possibility to start my lecture before 10:30, but I'm sure before 10:25, the previous speaker was there, so I cannot enter. So I can start thinking that from 10:25 to 10:35 is my expected time to start my lecture, but 10:30 is maximum, therefore possibility is maximum. You know, in mathematics, there is a theory, probability theory. All of you know probability theory. That is a kind of uncertainty. The thing we are associating the chance factor, and we are associating to say that this event may happen with this chance. That is the probability factor. But possibility factor is something else. In possibility, we say that this has already happened, but I do not have clear picture about it. Okay, that's why I am just associating possibility of happening of that event. So I am attaching the fuzzy measure to it. That is the difference between the probability theory and the possibility theory, probability and fuzziness. Now, again, I'm saying that is not my concern to explain today, because my lecture is not introduction to fuzzy set. My lecture is an introduction to fuzzy geometry. That's why we started to explain how we can define this fuzzy point. There we could see that if I just draw a line, you see there is a number, all right? And if I just move it like this, we can define this fuzzy point as a combination of these numbers all together, all right? And in other ways, geometrically, we can visualize the same thing. You just see, we are just putting a half plane here, and we are considering a cross section within that. Now, if I start point AB, fuzzy AB, and if I just put a half plane, say P theta, because it's making an angle theta with the base space, and if I just move it from 0 to 360 degree, we will get different triangular shapes together. Therefore, we can say that any fuzzy point is a combination of fuzzy numbers. We started visualizing that way, because if we visualize this way, we have seen that whatever definition we can develop after that, like line, circle, conic section, we could see that it will not lack inner conformity. It means that if we just translate it into the classical geometry, very easily we could do it. Because the difference between the fuzzy geometry and in the classical geometry is that in fuzzy geometry, we are considering the uncertainty level. And if we make the uncertainty level 0, then it will become the classical geometry. Therefore, our geometry, fuzzy geometry, must be something. If we just remove the uncertainty part, just like our probability theory, then it should reach to the classical geometry. That's why we started thinking fuzzy point this way. And you see, we are considering fuzzy number from different angular positions. But if you know fuzzy set theory, you see fuzzy numbers are always defined on the real line. How we can consider a fuzzy number which is situated at x equal to y. Therefore, we started thinking about the fuzzy number along a line because we are moving the line from 0 degree to 360 degree. So, we say that this is nothing but a simple transformation after rotation and no translation after rotation only with the degree theta. All right? And this is a simple expression. If there is a point from 2 to 4, that is a fuzzy number, where at 3 there is the maximum possibility. From 2 to 3, the possibility value is increasing from 0 to 1. From 3 to 4, again, possibility value is decreasing from 1 to 0. And if we just translate it, we could see that it will, instead of starting from 2, after 45 degree rotation, it will start from root to root 2. And 4 will become 2 root 2 to root 2. How we got it with this transformation only, that q equal to x cos theta minus 1 sin theta. This is because of rotation. And this is the translation, AC by x square plus b square. You know this mathematics very well. We have just applied this thing and we could define fuzzy number along any line in the Euclidean space, which is making theta angle with the real axis, with the x-axis rather. All right, because we have to define fuzzy point. And this is the mathematical definition. We started defining fuzzy point this way. This is the first initial part of our journey on fuzzy geometry to redefine fuzzy point this way. And we could say that any fuzzy point at AB could be the collection of fuzzy numbers p theta, but theta we have taken from 0 to pi, 180 degree, because if we just move from 180 to 360, we will get the same combination in the reverse way. That's why mathematically, just taking the rotation over 0 to pi will be sufficient. But geometrically, you should think that we are rotating from 0 to 360 degree, that way. And you see, we could say the membership function could be the collection of these membership functions together. Okay, and we could say that LP theta is a line passing through AB and having angle theta with the line L, that is joining between AB and C. That way we have defined fuzzy point. Now, Dubois-Prade in 1979, this is a very well-known theorem defined in Dubois-Prade book. You will see that, because we have to define fuzzy geometry in such a way that existing fuzzy theory should not be violated. This is one objective was for us, and another objective was, if we just translate into the customary, into the classical geometry, then it should give us a proper picture of the classical geometry that way. Okay, now you see, we started thinking the existing literature in 1979 defined by them, and we have used it. I'm not going into detail, but I would like to say that we started thinking how to add two fuzzy numbers. Whenever we are adding two fuzzy numbers means we are adding the numbers you see around 2 and around 6, it's going to around 8. And the range is changing from 1 to 3, 5 to 7, it's going to 6 to 10. How we are doing? We are taking, if I consider an interval, if you do not know fuzzy set theory, I would say that you may consider an interval from 1 to 3 in real axis, and in the y-axis you consider a membership function, and you draw it. From 1 to 2, you just draw the membership function from 0 to 1, and from 2 to 3, you make it 1 to 0. That way, similarly for 5 to 6 and 6 to 7. All right? And whenever we are considering the addition, it means that within those two intervals, from 1 to 3 and 5 to 7, in fuzzy set theory, it has been said that you consider all possible combinations. And for example, the combinations 2.25 and 6.25, how much it is? It is 8.5. 1.57, 8.5. 1.9, 6.6, 8.5. The first component is coming from the first fuzzy number, and the second component is coming from the second fuzzy number. But you see, this combination all gives 8.5, which lie within 6 to 10. All right. But how many combinations we will get? Infinite number of combinations we will get from here. But how to think about it? What are the effective combinations? It's not that we should take all the combinations together. The previous theory said that you take all combinations together, and from there you find out the maximum membership value where it lies. Max min operator they have used rather. But through our geometrical idea, we could see that all combinations are not effective combinations. And we have introduced a new concept that is called the same bonds and the inverse bonds between the fuzzy numbers. Those are responsible to define the effective combinations for doing the fuzzy addition, fuzzy subtraction, multiplication, and division, all these basic binary operations. All right, because this same point inverse point concept gives us the idea which will remove the problem of Buckley-Islami. Just you see the Buckley-Islami, whenever we are considering that you connect all points together, that will be the point where we are connecting like this. But connection would be within the same membership grade, that is for sure. The grades are given with the lighter circles in the right and the squares, like the different squares represent different membership grades. Different circles represent different membership grades. And the previous fuzzy set theory said that, existing fuzzy set theory rather said that you connect all points within the same grade of membership. It's not in proper form because the lines are crossing in between. If we just extend the lines further, it will give a different shape. According to Buckley-Islami, this is the fuzzy line between 3 points. But we say that this can't be. The line should not look like should not have a butterfly effect. It says that beyond the points, it will just spread like this. Then the inner conformity will lose. Therefore, our approach says that you connect all points in such a way that same points will connect to same points. Inverse point will connect to the inverse point for addition. That way, I'm not going into detail the mathematical notation. Just I will show you that how really we have done it. Very in a very rudely, bluntly, if we say that you see the two red points are the same points and two green points are the inverse points. If you ask me why it is so, we have defined mathematically that there is a basic line and the lines LP theta and LQ theta. The left part of it, of individual fuzzy numbers, the points in the same membership grid are the same points. Even in the right, the points from one fuzzy number to the other fuzzy number, and within the same grid, these are the same bonds. But if we consider the combination left to right, it will be the inverse point, or right to left, it will be the inverse point. According to Buckley Islami, it says that you connect all. That means red with red, red with green from one to the other. Then it will cross. The cross effect will be there. And we say, don't do it. Don't connect this way. We say that we should remove this cross effect. And we say that we should connect. I'm not going into detail of that. We should connect this way so that the left will be connected to left, right will be connected to right. And there is a mathematical definition for it. This is the mathematical that we know that we will get any point between given 2 points P1 and P2 if we take the linear combinations. For different value of lambda, we will get different point. We know in classical geometry. Here also we have said the same. And we have said that if we just consider that way, then the fuzzy line will look like this, where P1 is a point, P2 is another point, P3 is another point, okay? And with this, even the butterfly effect will not be there. Our approach says that combines only the same points. That means only the points which are in the same side, not in the other side. Then that crossing effects will be there. And Buckley Islami said, combine all points in the support. Support means the same membership value. That's why it was lacking the inner conformity. But our approach confirms that if we just reduce the uncertainty level, that means if we just squeeze the fuzzy points to a crisp point, our existing traditional conventional geometry will not hamper at all. That was the idea. Now there is a big theory behind it. I'm not really going into it. Just I wanted to show you the difference between Buckley Islami's approach and our approach. And with this approach, we could define the fuzzy line further. If we have different points, P1, P2, P3, P4, P5 of different shapes, even we can define nicely. And mathematical equation, we could define it very nicely. And that was the first challenge we could. And there are a series of papers we have published on this. And first paper showed about fuzzy point. If you're interested, you can see it in fuzzy sets and systems. And the second paper was on fuzzy line and the theory. Even you know, for the line in classical geometry, they are a different form, intersect form, and other forms as well, that is y equal to mx. And all the forms are defined here as well. In fuzzy sense, we have defined it. But here we also defined, if I just take any point, how a fuzzy number along that line looks like. That also we have defined on that paper. And these are all the notes on fuzzy line in the sense that we have defined the 2-point form, slope intersect form, and everything. And 2-point form looks like this. When two fuzzy points are given, fuzzy line, hazy band looks like this. Okay, and this is the corresponding definition for it. Therefore, if we just give any 2 points, fuzzy points, we can define a fuzzy line nicely. Because our target was to define a fuzzy curve that is still remaining. We are doing many works, but we have to do many research on that. If you get interested, you can also be involved in that. And if you want to join with me, you can also come forward and contact me for doing fuzzy geometry. I'll be happy to join with you. Now, this is the 2-point form, but in the we are considering the intercept of that line on x-axis and on y-axis, how it looks like. Point slope form we have defined there. Slope intercept form we have defined there. Slope intercept form, all of you know, when slope of the line is given and intercept is given, then how to define it. Okay. This is only the intercept form, x by a plus y by b equal to 1. But the fuzzy line looks like this. It is given in that paper, the second paper of us. Okay, and we have defined the interrelationship between those. These are all about the fuzzy line, you see, and we could see. But the question comes, if two lines are there, for example, the lines in the xy plane, one is given 2, 3, 5, 6, and another one is given, say 2, 3, 5, 6, and 8. And if I say the 4, 10, and here if I say that the 4.5 and 1, that means two lines will cross each other. Then if the question comes, what will be the fuzzy point which is situated in the intersecting region? Okay, that is a question, and we have solved it in another work. For example, there is a fuzzy line, there is a point not on the line, somewhere else, and if I want to draw a perpendicular line from that point to that line, then what should be the mathematical equation for it? We have worked on it, but we haven't worked yet that if there, instead of a fuzzy line, if we have a fuzzy curve could be parabolic, elliptic, anything, and a fuzzy line is touching there, then what is the meaning of touch, and what is the term touching point, the tangent? If the line is a tangent, then what will be the fuzzy point which touches the elliptical curve or parabolic curve with the line? That part is yet to do. Lot many works are remaining, but we have started our journey with these definitions only. Now, as I said, perpendicular fuzzy lines. For defining this intersecting point, you see why we have defined this way. The intersecting point could take different shape even, but why we have done so, that logic is also given, because our objective was we should not deviate from our existing fuzzy shape theory. This is the first objective, and the second objective was our theory should be such that it will maintain the inner conformity. That means if we just define the same thing with zero uncertainty, I should reach to the classical analytic geometry. That's why we thought that way, and we could see that with those objectives, this is the intersecting point. There is a paper on this. Just you see, you will get it if you are interested. But again, I'm saying, if instead of two lines, if these are two curves, then what will happen? This work is still, we didn't do it. We have to do it. If you want to join, you can also join there. This is a nice work, and the series of work will come out from here. Now, if we just brief it in the fuzzy line, what we have done till that, in our study, we obtained the following properties, the fuzzy lines. If these are extended by infinitely, then how it looks like. That means we have defined fuzzy line segments. We have defined fuzzy line when the line segment will be extended by infinitely. If a line perpendicular to the core of another fuzzy line, then along that line, what is the fuzzy number which exists on that line? We have defined it. A fuzzy line is always normalized. and more precisely, its core is always crisp line. And we have said as a whole that a fuzzy line can be perceived as collection of crisp points with varying membership values, collection of fuzzy points, collection of crisp fuzzy line segments or half lines for line segments or lines. That means we wanted to say that in a hazy, just in classical geometry, 2 points can be connected with the minimum distance as a line. Here also we did the same. 2 fuzzy points we can connect with the fuzzy line segments. And this is nothing but a collection of crisp line segments or crisp half lines, we say it. Then we started thinking how a fuzzy circle looks like when the center has been given and the radius has been given to us. That means center is given as a fuzzy number. Center is hazily defined. Even it has been said the radius is also fuzzy in nature. Then how it looks like? We saw it looks like this. Hopefully we'll accept because this is a hazy circle. Okay. But you could see that there is it is very much uniform in nature. Is it always so? For fuzzy circle, not really. Then we have defined the fuzzy triangle. One thing I forgot to mention that fuzzy point can take different shapes. It could be circle, it could be elliptical, it could be rectangular, it could be square. Any shape it could take which depends on the uncertainty along x-axis and uncertainty along y-axis. Here we have considered 3 points. One is the circle, another one is the ellipse, and another one is the rectangular. And we have defined, since as we say that we have defined fuzzy circle, as we say that we have defined fuzzy triangle, this is the construction I have showed it to you. But along with this, we have given the entire definition of it. You will get it in the literature. We have done it. Not only the process of construction as we do in geometry, but also the closed form of individual fuzzy objects we have given for this. Now, you see, here it has been given that we wanted to say that a fuzzy triangle whose sides are 3, 2√2 and angle is 45 degrees. How it will look like? Can you think about it? We have defined these 2 fuzzy triangles are similar triangles. And we have defined the property of similarity as well. Because we know how 2 triangles can be similar triangles, how 2 triangles cannot be the similar, and when we will define it as the equilateral triangle and the other properties, we need to do more on it. We have just introduced the concept of fuzzy triangle and few properties of those, but still, if you ask me that whether we have completed, not really. Further research is possible in every topic here. Just as we did in the classical geometry, same thing we can develop for fuzzy geometry, but we haven't done it. And because this is not only one person can do, this is something, the idea we have floated now, this is the responsibility of all of us together rather, to take the concept further. Now, you see the fuzzy circle with 3 points. It is not uniform in nature. It will look like this. You could see this is a fuzzy circle. There is no doubt about it because there is a intense black circle in between, but the haziness differs. Somewhere it is the uncertainty is more, somewhere the uncertainty is less. Why it has happened? Because the points which are lying, 3 points are given, 3 points are having different shapes. All right. Because of this, it is happening. The theory behind it we have developed there. And this is the fuzzy parabola also. We have just introduced, not really for the theory on it. But you see, as I said, more works can be done. But we have, after developing fuzzy geometry, we have applied fuzzy geometric interpolation theory. We worked with the exponent and the real expert, Professor Laszlo Koczi from Hungary. I am saying exponent because he is the initiator of doing the fuzzy interpolation. You will see many publications of him and his students on fuzzy interpolation. His age is now around 75 or so. We are still working on with him. Now, we have applied fuzzy geometry there, and he was so happy to get the results, which he did it algebraically, but we explained the same geometry. He said that this is very much useful, the fuzzy geometry, because it gives us the visualization of the fuzzy interpolation. And geometry is something which gives us the visualization of the objects. That's why our journey is still going on. And we have started in this line another very complex work, that is non-convex geometry. Here, whatever fuzzy points you have seen, these are convex in nature. But if the point is non-convex, then we will reach to a very complicated situation. We started working on that as well. And these are all about I just wanted to say to you. Thank you. And if you have any question further, you can ask me. I'm open to you.
Thank you, ma'am, for a nice presentation. And like one question that come to my mind also, and one presenter, one listener, she also asks the same question, that if we you define the circle, no? You define the circle. So if we want to define the sphere on this fuzzy geometry, can you define it? What are the challenges?
Yeah, we can do it. Yeah, one thing you have to think about it, that whenever we have done in the 2-dimension, because why? Because of we wanted to visualize it, and in 2-dimension the object is there, in the 3rd dimension the membership function. So we could see the 3-dimensional object together. Now, whenever you are defining the sphere, that means the object itself in 3-dimension, your membership value will go to the 4th dimension. Geometrically, you cannot do it, but mathematically, I can say that the same theory is applicable there.
Okay, like this, like we know that there are type 1 fuzzy, type 2 fuzzy, type 3 or type n fuzzy.
Yeah.
So like this line concept is associated with the type 1 fuzzy only, right?
Exactly. You
And
can extend it for type 2.
Circle is for, okay, these definitions can be derived for type 1, type 2, type 3.
You have to redevelop the whole theory for type 2 and type 3.
Okay.
But this would be the basis, at least.
Okay. So any other question from the audience?
How can we define the distance between two fuzzy lines in fuzzy geometry? Yeah, if you see, we can do it. In the existing theory of fuzzy geometry, it has been said that the distance between two fuzzy lines is fuzzy number, crisp number. But it can't be, as you have seen that the line itself hazy in nature. So we have defined it. If you see the paper, you can see it. I don't have the equation ready with me at this moment. Yeah, there was another question. It is there. Already we have defined it. Yeah, was that audio was breaking?
Yes, ma'am. It was like the initial.
Oh, but in the
Now
full
it is
lecture
okay,
or
but
some part of it?
like in the initial of your talk, the audio was breaking.
Oh, maybe because of network.
Now it is fine.
Nowadays, there is a lot of network problem. Yeah. Now, the another question, what will be the challenge when you move to 3D geometry? I have answered it. Second question from Tushar, for graphs, which software I use it? For graph, we have written the program on MATLAB. Whatever figures you are seeing, these are all the programs we have written with MATLAB, and we were getting the corresponding object from there only. How we can define distance between, that I have answered. Which software for most useful in mathematical modeling? MATLAB is very good. MATLAB, Mathematica, these are very good softwares. What can be said about the radius of a fuzzy circle? Fuzzy circle radius will be always fuzzy in nature. Will be a fixed positive real number? It's not a fixed positive real number. It will be a fuzzy real number. Okay. This is the way I can just give your answer. If you have further question, you can ask me.
Excuse me, madam.
Yes.
Madam, fuzzy interpolation, can you describe?
What is the meaning of it? Huh?
Yes, ma'am.
Interpolation means, for example, it is very much applicable in engineering theory. That there are certain rules. Rules means a machine will work in a good condition if the temperature is this, humidity is this, and the other parameters, say some other parameter is this, then machine will work good. This is the first rule. The second rule is if the machine will work bad if the values of the temperature, humidity, and the same parameter in a different way. In that way, we have given different rules, that the working of machine in good condition, excellent condition, bad condition, medium condition, like that. Therefore, if somebody is saying that this is the temperature, this is the humidity, this is the value of the parameter, then the rule will tell us that whether how the machine will work. But you see, what is happening, if the temperature is given such value which is not given in the rule, if the humidity is given a value which is not within the rule, it may happen that it is within the good and excellent conditions, some value combinations have been given. In that case, interpolation, just mathematical interpolation, works very nicely. Now, fuzzy interpolation is just the same rule we have defined in the Professor Coetzee defined long back in the fuzzy environment, the same rule base, and they define fuzzy interpolation there itself. And our job was to describe the rule in the geometrical plane and use the geometry to define the fuzzy interpolation in a better way. Okay, that was the case. Am I clear?
Yes, ma'am. Thank you. Thank you so much.
Thank you, ma'am. Thank you for being here, and we believe that in future also you could be here in the beautiful campus of Tezpur University. And
yeah, I'll be happy to go to your campus. I went once, but I want to go once more.
yes, since this is pandemic, so we could not do it.
I know.
So yeah, we have our next speaker also, Professor Manoj Kumar Jadhav from HRI. So with your kind permission, let us call my
yeah. Thank you very much.
Professor Rajat Kanti.
Okay. Good morning, Dr. Deknath.
Good morning.
We are still before time. Actually, our exact session should start at 11:45. Should we wait some more time? Dr. Devnath?
You may start since Shari is waiting and Shari is here. So you may
Okay,
start.
okay. Thank you. So let me welcome to Professor Manoj Kumar Yadav in this session with a brief introduction. Professor Manoj Kumar Yadav did his PhD from Kurukshetra University, and then he joined in Harishchandra Research Institute. He's a professor there. Professor Yadav also member of editorial board member of Proceedings of Mathematical Science, and he is a member of National Academy of Science. He is a recipient of Indian National Science Academy Medal. He has completed several projects from DST and have already published many papers, more than 30 papers in the most reputed journals like Journal of Algebra, Journal of Group Theory, Journal of Algebra and Applications, then journals like International Journal of Algebra and Communications in Algebra. He has produced 5 PhDs, and he has also visited foreign universities like as a visiting professor of universities like University of Florence. So it's our pleasure to invite him in this conference. So I request Professor Yadav to deliver his talk.
Thank you, Rajat, for this kind introduction. And I thank all the organizers for inviting me to speak at this occasion, particularly Rajat. And let me share my slides. So I suppose my slides are visible.
Yes, it is visible, but two slides in one frame. Yeah, now it's probably good. Yeah, it's good now.
All right. So after this a wonderful talk by Professor Chakravarti, I am not sure I will be able to do justice with the audience. This was very nice talk, but mine will be a bit abstract, but I will try to make it as easier as I can. Certainly I cannot avoid some intricate concepts from group theory, but I will not get into the technicalities, neither I will bombard you with many theorems or lemmas, although there will not be pictures, graphs and diagrams. It will be all kind of text, but let us see how can I go. So the title is Skew braces and solutions of the Young-Baxter equation. So let me give a brief introduction to this, in the sense that I will only use some terminology. I am not an expert on the application part of the material I'm going to present. So the Young-Baxter equation, or more precisely the quantum Young-Baxter equation, was introduced by physicists Young, C.N. Young and R.J. Baxter in the last century. Young is a Nobel laureate in physics, and he is now 99 years old but still alive. Baxter is much younger than Young, I mean 80. And so while studying integrable systems and the other concepts in statistical mechanics, first I think it was introduced the classical Yang-Baxter equation, and then it is a quantum Yang-Baxter equation, which is the quantum integrable models. So the interested reader may read this stuff from the internet or from other sources. So I have no more ideas than what I have said. I never try to dig into the concepts, but I certainly will do it in future. I'm also new to this subject, and it's only 3 to 4 years when I started exploring the topic. So in this talk, what I'm going to do is study the solutions of the Yang-Baxter equation. And the solutions have applications in physics, as I mentioned, in integrable systems, many body problems, in statistical mechanics. And more importantly, these have connections with many mathematical concepts like Hofg-Alva structures, Weber-Busch groups, groups of I-type, and in Lie algebra, bialgebras, associative algebras, and so on. As I told you, I'm not an expert on all these areas, so if you ask a question about this, I may not be able to answer you. So the solutions of the quantum Yang-Baxter equations have been studied extensively in the literature. And it was 1992, let me start. The Drinfeld actually suggested that instead of studying solutions, one can just study set theoretic solutions and then extend those solutions to the solutions of the Yang-Baxter equation. So before I tell more story, let me first define what does one mean by a solution of a Yang-Baxter equation, quantum Yang-Baxter equation. So I start with the vector space and take its third tensor power. So the tensor product of vector spaces or any field is well defined. So if you don't remember what does that mean, don't worry, because we are not going to use it. So if you know it, then it's fine, good enough. So take 3 copies of a vector space, take their tensor product, and then take their endomorphisms. Endomorphisms are just homomorphisms from V third power tensor to itself. We don't have any more condition on that. And so the quantum Yang-Baxter equation is the following equation. So it takes place in the endomorphisms of the third power of the tensor of V, and Rij denote the action of R in the endomorphisms in the second power of the tensor product of V. So this simply means that we have an endomorphism from V tensor power 3 to itself. Then you just declare that, so this define an endomorphism which works as an identity on the first component, that is called R23. And if it behaves like an identity on the third component, we just call it R12, and similarly R13 if it is identity on the second one. And so if there is such an endomorphism satisfying equation 1, so that is called a quantum Yang-Baxter equation. So what is called a solution? We say that a linear transformation, because these are vector spaces, you can just call them linear transformations, R from V tensor power 2 to itself is a solution of the Yang-Baxter equation if R satisfies this quantum Yang-Baxter equation. So this is a very simple thing to understand, that if there exists an R from V tensor power 2 to itself such that equation 1 is satisfied, then we say that R, that linear transformation, is a solution of the Young-Buxton equation. And so we would like to familiarize this concept with algebra. Of course, this is also algebra. So more precisely, I should say the group theory. And before that, what did I tell you already? It was Drinfeld in 1992 who suggested that one can understand set theoretical solutions to understand the solutions of the Young-Buxton equation. This simply means that you know that if you're starting with a vector space, instead of that, you start with its basis of this vector space, that is a set. And if you construct solutions on that set, then those solutions can be extended linearly to the vector spaces. So that is the idea. And so we will be talking about set theoretic solutions. And I will now never come back to the vector spaces in this talk. And to simplify notation, we say that this YBE for abbreviation for the quantum Young-Buxton equation. So whenever I say Y by E, mostly I will speak Young-Buxton equation, and that simply would mean that I am talking about quantum Young-Buxton equation. The quantum Young-Buxton equation is the one represented by the equation 1. All right, so let us set the scene for the sets. So here X is any non-empty set, and Xn is the Cartesian product of n copies of X. And I will be using only n is equal to 2 and 3. So we say that a mapping R, this just map a function here from X squared, the Cartesian product of X with itself, to X squared is a set theoretic solution of the Young-Buxton equation if the same equation which I stated for the vector spaces is satisfied, where Rij has again the usual meaning that at Ij position this is R, and the remaining position it is identity. So this equation again holds actually in X3, not in X2. And in this case, we say that X along with this mapping R is a set theoretic solution of the Young-Buxton equation. So I hope I am making sense and the concept is clear. Please let me know if there is any doubt about the definition, because it is important that you grasp this definition before we go ahead. So our ingredients are a non-empty set, the Cartesian products, and then a mapping R from X square to X square, satisfying this property where Rij has this meaning that Rij is R and the remaining component is identity. And so this equation should be satisfied. And now we are going to reduce this or exchange this equation by another equation which is more familiar to group theorists. It's called a Braid relation. So this comes from the Braid groups. And if you want to see an example before I define it, for example, you take S3, the symmetric group on 3 letters, say 1, 2, 3. And then you notice that this group is of order 6. And this consists of all permutations on 3 letters, 1, 2, 3. The composition, the operation on the group is the composition of the permutations. And this group is generated by the transpositions, you can call 1, 2, and 2, 3. So 1, 2 is a permutation which takes 1 to 2, 2 to 1, and 3 is fixed. And the transposition 2, 3 is the one which takes 2 to 3, 3 to 2, and 1 is fixed. And you notice that if you take those transpositions, then this equation will be satisfied. So R12, R23, R12, R23, R12, R23. Just call that permutation R12 as a permutation which takes 1 to 2 and 2 to 1, and fixing 3. And then 2 to 3 simply means that 2 to 3, 3 to 2, and 1 is fixed. So the concept actually comes from that sort of, because this is nothing special about S3. You take any symmetric group on a finite set, and then you will notice that if this group is generated by the transpositions of the form 1, 2, 2, 3, 3, 4, so the I plus 1, and then you notice that if the generators are a little far apart, then they commute, but if they are side by side, then they satisfy these conditions. All right, so a function R from x2 to x2, the Cartesian product, is said to satisfy braid relation if R12, R23, R12 is equal to R23, R12, R23. Whereas I explained earlier, R12 simply means this R, where the identity at the last position, and 2, 3 is R identity at the first position. And one can replace the quantum Yang-Baxter equation by this equation with a little effort. That effort is here. Define this permutation map. So this is just a map which permutes the entries. So tau prime xy goes to ix for all xy and x square. And then if you define R is equal to the composition of this capital R with tau prime, then you notice that so this R satisfies equation 1 if and only if small r satisfies this equation in small r. So it says that XR satisfies braid relation if and only if X capital R is a solution of the Yang-Baxter equation. So for this talk, I will be mainly considering braid relations and not the.
भैया का सेटअप कर दो थोड़ा सा सोफस का ना कर करो
There is some description.
लाइट कौन सी वाली जल रही है दिखाओ ये वाली जल रही है ना
Mahendra Singh, please unmute yourself. Mahendra Singh.
Rajat, you can unmute. All right, I think it got settled. And all right. So as I said, not yet.
Yes,
So,
sir, please.
yeah, so a function from x square to x square can be written in this form. This is just a component maps. So if you have for every x and y, you have rxy. You just then compute the values, and the components you just denote by these symbols. And these symbols are going to be important for us. So obviously the sigma x and tau y are maps from x to x. And now we specialize to these things. So a solution x small r of Yang-Baxter equation is said to be non-degenerate if both sigma x and tau y are permutations of x. These are 1-1 functions. And I hope you understand the meaning of non-degenerate, because here they are in some sense going to that kernel business, because these are just sets. So the kernel does not make much sense, but there is some kind of idea you can have from the non-degeneracy in vector spaces, maps in the vector spaces. Mainly it occurs in bilinear maps. So XR is said to be involutive if R square is identity. So just apply R again, you get the identity map on X square. And now for many slides, we are going to talk about only is involutive non-degenerate solutions of the Yang-Baxter equation. So before that, I defined the isomorphism between two solutions, and that is usual stuff. Two solutions are said to be isomorphic if there is a bijection between x and y, which is compatible with the maps R and R prime. So that's what does mean by the compatibility. You apply your function R first and then apply phi, or first you apply phi, go to y, and then apply R prime, you should get the same thing on both sides. So that is the compatibility condition. And if this happens, then we say that the solutions are isomorphic. And this concept, I will not use it heavily, but the point is that when we come to the concepts of skew braces, then the concept called isomorphisms of skew braces, then they will give you the isomorphic solutions, and start with isomorphic solutions, and then if you get the skew braces, you'll get isomorphic skew braces. So there's going to be one-one correspondence between the non-isomorphic solutions and the non-isomorphic braces and skew braces. So you'll see it. So let us see an example. In the example, this one is the very trivial example. This is called a trivial example actually, because just permute the entries. So Rxy is equal to Yx. So at the braided relation level, this is xy going to yx. But if you transport back to the Yang-Baxter level, capital R, then you will see that it will be just xy going to xy, because you know that we have modified our capital R by this permutation. So divided back, you will get the trivial solution. That's why it is called trivial solution. And if you know some solutions, then you can take Cartesian product and you can construct more solutions. So that's the other. This is not in some sense a good example, because for this example you should know at least two examples. But you can take trivial examples, take the Cartesian product, but that is again going to be trivial kind of business. But let us see a non-trivial example. Here it is. This, I think you all can understand this. So z square to z square. Z is the set of integers. And the z square simply means that z cross z. So this all integers of the form a comma b. A and b are integers. And define this map Rxy to y minus x, x plus 1. So it is not difficult to check that this will satisfy the braid relation. But that certainly requires little checkup. But the involutive part, that is the R square, is identity is clear, because if you apply it again, so what are you doing? You're just reverting x, y, and putting minus in the first place, plus in the next place. Then you revert it back. It will be x plus 1 minus 1 and y minus 1 plus 1. So it will be xy. So this is a kind of non-trivial example of a solution of a Yang-Baxter equation, which is non-degenerate and involutive. All right. Now, we have just talked about solutions of Yang-Baxter equation starting from a set. How would one get into the algebraic structure from this information? That's what I'm going to do now. I'm going to associate a group for a given set theoretic solution, which is called the structure group of the solution. And for this structure group, all our solutions are going to be non-degenerate involutive. And here is the construction. Start with a solution. The structure group of XR is defined by. So I hope this expression makes sense. Of course, for group theorists, it makes sense, but I want to make all of you a bit comfortable with this notation. So what I'm going to do here, GXR is just notation, and this side is triangles, and X is this set X. And so what does this mean? Simply means that there is a group, free group, Again, I'm really sorry, but let me try to explain it. So the free group generated over X. What does that mean? So you take any set and you now take the words where the alphabets come from X. So for example, let me just take the simplest case. Let me just fix any a small a, and then all possible words in a. So that they will be something like a. That may not make sense at starting point, but then we note it by a, or it might happen that then introduce inverse sign a inverse. A and a inverse are just symbols. Now start making sequences of these words, putting one after other. A inverse, a inverse, a inverse, wherever you want, finitely many at one go. And then make a set of all these this is called words. Make a set of all these words. And then you can define an operation on it, the juxtaposition. Juxtaposition, simply take a word, a sequence, take another sequence, put them together. It will again be a word. And then you need to reduce these words, simply meaning that if A and A inverse come all together, just forget. So delete all these kind of things, and then that will become a group actually. And that is called a free group on that element A or that symbol A, and that is isomorphic to Z. Integers. Integers with addition is an infinite group. This is commutative, because when you add in any order, so if you take more than one element, A and B, and do the same thing, so A, B, then A inverse, B inverse, these are 4 alphabets, and then you take all possible combinations, A, B, B, A inverse, B, A inverse, B inverse, A inverse, B, B, A inverse, whatever way you want, and you just collect all these kind of objects, and then reduce them, meaning again the same, if A inverse comes all together, or B inverse comes all together, just forget this, and then again take the operation at the juxtaposition. It is going to be a group. It's called a free group on 2 letters A and B. These are all infinite groups. In this case, it will not have abelian, because there is no relation. In some sense, vaguely speaking, we say that a free group is a group which do not admit any relations except the obvious ones. Obvious ones simply means that A commutes with its powers and A commutes with the identity element. And so take the free group generated by X, and then these are the relations. You notice that all these elements, X, Y, sigma X, Y, tau Y, X, these are all elements of that particular group which you have constructed, because these are elements of X or their inverses. And so you take these relations and factor your group by the subgroup generated by the normal closure, normal subgroup, max, smallest normal subgroup, and then in those subgroup. I hope I am making some sense at least. So this is that group. So from a given solution, you get a group, which is called the structure group. And this group can be given some structure, which I will be calling is a left brace. So I will let us go ahead and let us first see an example. So if the trivial solution, if you take xy is equal to yx, then the structure group is this Z super X. This is the free abelian group generated by X. I explained you how a free group on one generator looks like. That is actually isomorphic to Z. And if you then take more elements in that set X, and if you put the condition that xy is equal to yx for all x, y in X, then you just, in the free group, you put the relation commutativity. That is called a free abelian group or free commutative group. So that in this case, that is going to. And I'm sorry that if this relation is not this relation, the commutative relation, then there will be that group, whatever group that will be, it is not difficult to write that down, that group. And this is a wide open problem to understand the structure groups related to the various solutions of the Yang-Maxwell equation. And the people are writing papers. So every month, the papers are coming on the structure group and related stuff. So this is a wide open area, quite new area. And this is not more than 20 years old, but certainly the substantial progress has been made. Many good results have been published. Still, many more are awaiting answers. So I am not sure whether you completely grasp this concept, but you may go back and see. So what more one can say? In general, as I said, in general, for a general solution, it is very difficult to say anything about the structure group, but there is a relation. Relation is this. So whatever X you take, whatever solution you start with, you can always define a map from the structure group to this free abelian group on X. In the particular situation, when we start with a trivial solution, this is an isomorphism. But for others, it is never going to be an isomorphism. And so this map will satisfy very nice properties. First of all, this is a bijection. The 1-1-on-2 map, and Gx are actually X on Zx. It's a group action. I did not explain this intentionally because I think that would have been a bit heavier. So, but I tell you that Gx are X on this group, and by an action, I simply mean that there is a homomorphism from the group to the permutations of the set. And this is equivalent to defining a group action by writing Gx on X. If G cross, there is a map from G cross X to X, satisfying certain properties, but that is equivalent to saying that we say that Gx on a set X if there is a homomorphism from G to the permutation group on X. And so we here have an action, and if there is an action, then this pi, the map pi, satisfies this relation. Satisfies this relation, which is called a cocycle relation. So one cocycle relation. So pi actually is a one cocycle, and this is a very important information, a very classical result by Ittinghoff, Sadler, Soloviev, and using this equation, they in 1999 proved that if the solution is finite, then Gxr is a solvable group. In Neutrum again, for group theorists it is well known, but let me explain it. So you take a group, you take its commutator subgroup. What does that mean? Is that you take all elements of the form X inverse, Y inverse, XY in a group, collect all these kind of elements, X inverse, Y inverse, XY, generate a subgroup by this set. Generating a subgroup simply means that you take all possible combinations of the elements under the operation of the group. That subgroup is called the commutator subgroup. Now you do the same thing for this commutator subgroup. Now replace the original group by this commutator subgroup, again define commutator subgroup, and keep doing this. If this series of subgroups becomes trivial identity at finite stage, at some finite stage, then we say that the group is solvable. Otherwise, it is not solvable. And interestingly, I hope you all know that this Galois theory, solubility of non-solubility of Quantic equations by radicals, which was answered by Galois long back, uses the concept of solubility. So these extensions, the group field extensions, this Galois group associated to it, and then the solubility of the equations actually has a great deal of connection with the solvability of the Galois group. I hope you all have read this masters in the course of algebra. All right, so there's a side remark. And now from this GXR, we have these maps, which y to tau y. Tau y, I hope you understand, this is a tau y, and this is sigma 1. So this is a map from X to symmetric X, which can be extended linearly to GXR, so we can get a map. And you can then define the quotient. The quotient is a group which is called the permutation group of the solution. And if X is finite, then GXR is also finite. How do you know that? Because if X is finite, then here you look here. If X is finite, then symmetric X is finite. There is no guarantee that GXR is finite, and mostly it is not. And I would say that it will never be finite, but this is always finite. But if you take the kernel, and you know that the GXR by kernel is embedded inside symmetric X, so that must be finite. So the permutation group is always finite if X is finite. And so because of this result, GXR is solvable. So the permutation group is also solvable, and we are going to make a very important remark on this little down. All right, now comes the concept of braces. So let me first define it. So let's say, like ring theory, there are concepts of like left module, right modules, and that kind of stuff. So here also define a left brace. So left brace is a set G with two binary operations, which we denote by plus and dot. So under plus and under dot, this is a group, and under dot plus is abelian group. So G plus is abelian, G dot is any group, and if this condition holds. Please try to see, this is something like a distributivity condition in a ring, right? But this is not, so this kind of semi-distributivity condition. So if this holds, then we say that this G plus dot is a left brace. So right brace you can define if you take the distribution from the right. But we will be mainly using about that left stuff. And so then we can define homomorphisms of braces, like the homomorphisms of rings, and then kind of define kernel. And the one interesting thing is that in this brace, the additive identity and the identity with respect to dot, they are going to be the same. So 0 and 1, if you just say 0 with respect to plus and 1 with respect to dot, 1 and 0 are same here. So that's what I have written. And kernel of F is a left brace. Then one can define some maps. I will tell you more about this a little later. So the ideal, we can define ideal of a brace like ideals in rings. So a normal subgroup I of G dot is said to be an ideal if these map, either this or this map stabilize I. So I don't know whether it's called stabilized, normalized, perhaps normalized, because if you take B from I and A from any element of G, then row AB is in I. So you can also equivalently say that if this happens for lambda, then it's also fine. And so ideals are again left braces, and ideal is a normal subgroup of both of these groups, because G plus is abelian, so every subgroup is normal. So you can define quotients here, and this is also a left brace. So if G is a left brace, take an ideal, take the quotient, get again. So there are constructions for many more if you have one. Let us see some example. The trivial one, let any abelian group, G be any abelian group, and define a dot, just A dot B is equal to A plus B. Then G plus dot is a left brace, which is called a trivial brace. Non-trivial brace, let me just show you. So start with a group of order 6. If you are a group theorist, you can easily understand it. Cyclic group and multiplication you define by this table. So this is the first observation which we made 3-4 years back when we started working on this area. So we took, I think, almost 1 day in constructing this table, because you have to consider all possibilities. And so this is, notice that is in non-abelian. So, and this is a non-trivial example. All right. You can construct braces from radical rings, ring theory. If you know ring theory, then start with a ring, and a ring is said to be radical if you can always define another operation on ring, which by this method, R circle S is equal to RS plus R plus M. If under this operation R becomes a group, then we call it a radical ring. It has equivalent other definitions, but I would only like to mention this one. So once you have a radical ring, you can now define a brace, which is a left brace as well as a right brace. And if you have a brace, you can define a radical ring. It's both sided. So if you're a ring theorist, you can explore braces. And then this map, which I have said earlier, is very important. You can define lambda AB. A, this is actually dot A dot P minus A. And this is an automorphism of G plus. Automorphism is a homomorphism, which is 1, 1, and 1, 2. So this is an automorphism of G plus. And if in a start with the left brace, I'm going to tell you how one can construct a solution from a left brace. So start with the left brace, then define a map R from G square to G square by this method, using this lambda map. So Rxy is equal to that. And one can then check that this is going to be a solution of the Yang-Baxter equation. Yeah, this is a little check. Not very trivial, but one can sit and try to calculate, then one can see that this satisfies the Brent relation. So from a left brace, one can construct solutions. From a solution, you can construct the structure group, and structure group can be made into a left brace, which I did not explain. And so Rajat, I think I am not doing very well with time. How much time is left?
Sir, you have still time. You can take your time. Our next session is at 12:45. So you can go up to date if you need.
Okay, okay, all right.
We have enough time.
All right. I hope I am not rushing. So
No, you're quite well.
yeah, okay, good.
You may go a little slow also, no problem.
All
You
right.
have time to.
Because I think that there is no point in rushing through.
Yes, yes, sir, yes.
So, so start with a left brace, which you can construct from radical rings, and then you can define a solution by this identity, and so that solution is called associated solution to the left brace. And then how there is a theorem which says that how can you go back and forth. So start with a solution, you can define structure group. On this structure group, you can define a plus sign, because this structure group is not abelian. So whatever operation that comes with, you define a plus sign with certain rule. So it becomes a left brace. And if it is a left brace, then you can go back as I have explained, because if it's a left brace, then you can define a solution. And the good thing is that you notice that start with this x. This is a finite. GXR is infinite. So this is an infinite skew brace. And if you define a solution with this skew brace, it is going to be infinite. But then this theorem says that you can always find a subset of H and a map S prime such that this solution Y S prime is actually isomorphic to the given solution. So that's the beauty. That's how the solutions and the left braces are related. So this is a deep result, but I did not tell you anything about the proof. but gave a general outline how things go around. So now there is a concept called involutive Young-Baxter group. So I can rush through it because this is not very important for this audience, because the point is that the permutation group which I defined. So you took that structure group. From structure group you go to the symmetric X, and then take the row as a kernel of row, factor the structure group by the kernel of the row, then you go to the GXR. That is the permutation group. And that permutation group, the theorem says that permutation group of a finite solution of Young-Baxter, a finite group G is a permutation group of a finite solution if and only if G is a multiplicative group of a left brace. So that's a very nice result. And so a group is said to be involutive Young-Baxter IYB if it is isomorphic to the permutation group of a solution. And so, as we have already proved that the permutation groups are solvable if X is finite, so that we can say that Young-Baxter groups are solvable. And Young-Baxter groups occur as multiplicative group of a left brace. So the multiplicative group of a finite left brace is always solvable. So you take any finite left skew brace, its multiplicative group is always solvable. And you know that the additive group is abelian, but there is a condition that the multiplicative group is solvable, but you cannot say more than that. And also then there's a question which says that whether every solvable group occurs as a Young-Baxter group, or equivalently, is every solvable group or maybe a finite solvable group occurs as a multiplicative group of a left brace, meaning if you start with a finite solvable group with some operation dot on this, can you define a left brace or define a plus so that that group with plus and dot becomes a left brace? And so that was a question, but it was proved in the negative by Batchelor. He constructed a P group of order P to the power 10. So this group is actually nilpotent, but it is not a multiplicative group of any brace. So you forget about solvable. Nilpotent ones there are counterexamples. The smallest P group satisfying this property is still open. So it is not known whether all groups up to order P to the power 9 satisfy this property. All right, so we have mainly talked about involutive non-degenerate solutions. And so as a summary, I say that there's a 1-1 correspondence between these two classes. So non-isomorphic solutions and non-isomorphic left braces are in 1-1 correspondence. So left braces actually captures involutive non-degenerate solutions, but not all solutions. And so for that, we really need to do something more. And that's what I'm going to do now. This is called a skew brace, which is in the title of my talk. A skew brace is a generalization of a brace. By a skew brace, I mean left skew brace. So in this case, now we start with two groups in which these are just groups. So earlier we considered that G plus was abelian, but now these are just groups. And we say that it's a skew left brace if this distributive law, the skew distributive law holds, or semi-distributive, whatever you want to call it, relaxed distributive law holds. So there you notice that this G1 inverse, which I just wrote by minus sign, was on this side, but here because there it was all right because it addition was abelian, commutative, but here it is not, so you need to put it here, otherwise it will. So a triple G plus dot with G dot and G plus any groups with this property is called a skew brace. So G plus we call additive group, G dot we call multiplicative group. And as I explained you, if G plus is abelian, then it is nothing but the skew brace, a brace, left brace. So the skew brace is a generalization of a left brace when you just take plus to be known value. And what is the beauty? What is the importance? Importance of this construction is that it captures all non-degenerate solutions. So involutive, non-involutive, all. And the basic facts again, the identity is coincide, so additive and multiplicative identities, and you can define this map. So please recall that there I write A dot B minus A because the group was commutative. Here lambda AB is defined A inverse. A inverse is with respect to the plus. And we are not going to use in this talk the inverse with respect to dot, which usually did not like A bar. But this inverse is with respect to plus sign. So this is a group homomorphism. And so because if it's a group homomorphism from G dot to G plus, automorphisms of G plus, but then you notice that element level G is same. So you take an element, say B here or A here, lambda A is an automorphism here, but if you just view it as an element of G plus or G dot, it doesn't make sense, doesn't make difference. So if you even consider this element A from G plus, then we are going to get a map. So the role of operation comes into the picture when you check whether it is a homomorphism or not. Otherwise, you can always define this map. And this map is very important actually, and I will explain you a little bit about this, why I'm making this statement. I feel that one can characterize skew braces using the properties of this lambda. Okay, let us see some examples. First example is again a trivial one. A dot B define B plus. So this, please notice that this is a little more than trivial, because there we said when plus was commutative, we just said A dot B is equal to A plus B. But here B plus A is not equal to A plus B because plus is not commutative. So this is not a trivial relation. So then you can actually define this skew brace with this plus and dot, and it is going to be skew brace. Let us see what is lambda map. The lambda map in this case is going to be very nice. This is conjugation by element A. And one can notice that if this map, will need small check that, and also view this map from lambda to G plus dot G plus, and it is going to be anti-homomorphism. And what is more important about that? The skew brace G, in which lambda is homomorphism from, so this is always a homomorphism from G dot to odd G plus. But as I pointed out, it is always a map, just a map from G plus to odd G plus, automorphisms of G plus. If it is a homomorphism from G plus also, then we call it a lambda homomorphic skew brace. And we have considered this recently in this paper, appeared in this year itself. So constructed lots and lots of examples of lambda homomorphic skew braces on free and variable, mainly in finite order. An interested reader may go to see the constructions. And other properties are considered in this paper. I will just, for this, to help the reader if they are interested in precise reference, here are the references. So this is about the construction, and this is about the basic properties. All right. So how skew left braces are connected with the Yang-Baxter equation. So here is the recipe. You start with a skew left brace, then you can define a function R by this lambda using again by lambda map, but this time this expression is a little more complicated than the case in left braces because the addition was commutative, so that this could have cancelled out there, but here it cannot be cancelled out. So it is a non-degenerate solution which in general is not involutive, and it is involutive only when then G plus is abelian, meaning it is involutive only when your skew brace is a brace. Otherwise, it is not. So, skew braces actually characterizes non-involutive, non-degenerate solutions of the Yang-Baxter equation. Yeah, this statement is not very precise because skew braces also contain braces, so you have to avoid the braces if you want to make this statement. Otherwise, you can say that skew braces characterizes non-degenerate solutions of the Young-Baxter equation, involutive, non-involutive both. And how now there is a connection with the group theory. How there are methods of constructing skew braces, and from skew braces the solutions. So I will just go through quickly the procedures. So G, for a finite group G, this is notation for the symmetric group on G. So G, consider G as a set, take all permutations on G, that will become a group, it's a symmetric group on G letters. And a group is said to be regular, a group G. So this G is different from the G because that was GXR, what was the permutation group, but this G is different. Of symmetric G is said to be regular if G action on G is free and transitive. You notice that this G is in the symmetric group, so there is an action involved in here. So the symmetric group not automatically, naturally acts on G, because if you take any set X, the symmetric X, the symmetric group on X naturally acts on X. So that's the action. So the every subgroup all of symmetric group G will also act on G, and so this action is free and transitive, then we say that it's a regular subgroup. And here is the definition of a free action. So only the identity subgroup stabilizes every element. Transitive simply means that there is only one orbit of the action. Simply means that there are two elements in the set. You can always find an element which takes one to the other. And it follows that the regular subgroup of the symmetric is of orders. So the orders are going to be same. So that's a fact, not a trivial one, but it's a fact. And then the holomorphism, it's called holomorph of a group G. Holomorph, you notice that the odd G, the automorphism group G acts on G naturally, and so take the same direct product. That is called the holomorph of G. Here is the definition. So holom G, and here is the product. So I don't want to spend much time on this because these are all standard stuff. Once you have this, then you can have the action of the holomorph of G on G. And here is the definition. So it's a bit little involved, but one can, if one sees it carefully, one can make sense. And that's what I have. So if G is a regular subgroup, then there exists an element here, because as I told you, this action is transitive. So for this element G and the given element G and 1, there exists an element from the element, the regular subgroup which takes G to 1. So that comes from the definition. And if you take the collection of all regular subgroups from the holomorph and denote it by reg G, all regular subgroups, set of all regular subgroups, then you notice that there is an action involved, and so here is the action. So group G, which acts on X, a subgroup H of G is said to be so the action was by conjugation actually. So you take a regular subgroup and take a conjugation from the holomorph of G, then it is really going to be again a regular subgroup. And so here is a concept which I will explain in this statement. So odd G as a subgroup of whole G is action closed with respect to the conjugation action whole G on reg G. This simply means that if you take sorry, so how would I go? There should be some sign. I'm very sorry. Can someone help? What has happened with this?
What is the problem, sir?
So I'm not able to see my screen because I just happened to push it on the right side and it went away somewhere on the right side.
So please stop your sharing and reshare your slides again. It will be
Okay, I think that is the best solution perhaps. And stop sharing. And then I need to open that file again.
yes, sir.
It's here. Okay. I will be finishing soon. So. Is it visible? Rajat.
It is visible, sir. Now slides are also changing.
All right, yes. So I was here. So this simply means that if you take an action, no, I think it wants me to stop perhaps.
Oh, no.
Yeah, anyway. So the action of whole G you take, you can always find an element of the automorphism group of G, so which have the same action, same effect on the elements of the reg G. So that's C closed. And so I proved that if this action actually is OUT G is C closed, and so this helped us to modify or generalize an algorithm proved by Vendramin and Grunieri for constructing or maybe enumerating skew braces and left braces. So here is the construction. So start with a skew brace, then A, lambda A is a regular subgroup of whole G, where lambda A is the homomorphism which I explained earlier. Conversely, if you have a regular subgroup, then you can define on this regular subgroup an operation dot by using this identity, and it becomes a skew brace. So this pi 2 and pi 1 are the projections on the second component and projections on the first component from the holomorph. Holomorph is nothing but the G semi-direct product of the automorphism group G with G, and then the projection makes sense. And so that's what we mean. And so we generalize an algorithm of Grunieri and Vendramin and proved this. So this is a result which we proved, and this really gives this algorithm. So this is the algorithm. Compute holomorph, compute the list of regular subgroups, and then using that regular subgroups, you can construct skew braces. I have not given this last one because it is a bit tricky. And so I'm not sure that it will be more interesting to display that relation on the screen. And so if just want to enumerate the number of skew braces of a given order, only first and second steps are sufficient. That's what I have said here. And these are the references. So before I go to references, I would like to make a comment that the Vendramin and Grunieri constructed braces and skew braces up to order, say, 68 or 67. But then we modified this algorithm, and then this modified algorithm became very, very fast, and we could construct skew braces up to order 868. And we could have constructed more, but we thought that, okay, how long one can go, because this is just a computational business. So, but our algorithm is quite efficient, and one can use it for constructing more braces. I hope it has already been implemented in the Magma and GAP packages, Sage packages called Young-Baxter. And there is a package called, as I said, Young-Baxter. Using that, one can construct braces and skew braces of given orders. I mean, there is of course a limit, but one can construct sufficiently large size. And here are references. Young and Baxter, the one who really initiated the work on Young-Baxter equation, and Tinkoff, Sadler, and Fillerer. And I think I will stop here. Thank you very much.
Thank you, Professor Yadav, for your very nice lecture on this topic, skew braces and solutions of the Young-Baxter equation. Any questions from audience?
I doubt.
Any questions from audience? So I just want to make some comment about this. As I know Professor Yadav, he was my mentor while I was a postdoctoral fellow in Harishchandra Research Institute. And from then I know his work. He was known for his work in finite group theory, theory of P groups, automorphism groups. But today I get some other field here. So I also wanted to know some applications of group theory. And today he has given a very nice connections of group theory, ring theory, and to this Young-Baxter equation. Sir, I just wanted to know, how do you get introduced to this field?
Rajat, I would make a vague statement here.
Okay.
Whatever has happened in my life was by accident. And so,
No, sir, it was very, very good presentation.
Good accident.
so this Valery Bardakov,
Yes, sir.
Valery Bardakov, he introduced me to the topic, my collaborator.
Okay.
And I will be happy if some of you would like to get into this. This is a very exciting subject. And all group theories certainly can take it because it is not very difficult.
So whatever solutions or groups we have seen, these are all infinite groups. Do you have some connection with finite groups?
The solutions which we constructed in that paper which I showed you, they are all infinite on,
Yes.
actually on free groups or free abelian groups. But I have also given some examples of order of order 6. And the construction which we took in the last one other paper is all finite, right? Up to order 868 we have computed. These are all finite. So there is a big challenging project of classifying braces and skew braces, finite size. And I would like to make a comment here that there are only 51 groups of order 32. But there are more than, I don't want to make a mistake, but let me just tell you this number, it might surprise you. This number, I think 12 lakhs.
Okay.
There are 12 lakhs skew braces of order 32.
So it's really a huge number.
Yeah. I mean, we are not even able to classify finite groups. So, I mean, it is a little bit hopeless to classify all skew braces, but people are enthusiastic on this project. I mean, certainly one cannot classify all, but we have recently done something on lambda homomorphic skew braces. And one can construct infinitely many classes of lambda homomorphic skew braces.
And for classification tools are only the computation tools or some other thing to use?
Yeah, I think to this point of time, I only know that the construction can be done through the holomorph, regular subgroups of the holomorph. There are no other methods. But theoretically, there are methods like the ones which I said, lambda homomorphic skew brace. You start with a group and a homomorphism from this group to its automorphism group, satisfying certain property, then you can construct a skew brace on that. There are theoretical methods, many, I think.
Thank you. Thank you, sir, for your talk. And I am sure that many of the participants can take this topic. As sir said that this topic is very new, it is hardly 20 years old. And there are lots of possibility of doing this for the pure mathematicians like who are interested in group theory and ring theory.
I have a comment on this. I said that set theoretic solutions is 20 years old, but the skew brace business is just 5 years old.
Okay, then it is even more interesting to work in this field.
I'm going to stop presenting.
Thank you, sir. Thank you for your presentation. Sir, I mentioned one more thing. Manas sir visited Tezpur University long back in 2012 probably, and we are happy to invite him again in our campus after this pandemic is over. Thank you, sir.
Yeah, I will be glad to come back because my wife is very much interested in visiting that part of the country. So she actually remembers you because you told that story of that bird. So that the female bird is inside, the male bird is killed by
Yeah. It is in Dhanesh.
the lady bird and baby kills inside the hole.
Yeah, this is the story of Hornbill.
Hornbill. Okay.
Hornbill.
They just die there waiting for their parent, that other part.
Yes, sir, it happens in.
So that is a very touching story.
Yes, definitely. This time, if you visit, I will visit you Kaziranga, and there you probably see the bird hornbill.
Okay, yeah, that will be great. Thank you very much.
Thank you, sir.
Thank you so much.
Thank you for inviting. So I will be here for the next talk. So you
Yes, sir, we are glad to
go over to the other one.
Next talk will be by Professor Irfanian. Let me check whether he has joined. He has already joined probably. Yeah, sir has already. Professor Irfanian has already joined to us. So Vijay, can we start for the next session?
Yes. Please go.
Okay. So let me welcome all to this session again. We have Professor Irfanian with us. Let me introduce Professor Irfanian to all the audiences. Professor Irfanian is a professor in Ferdowsi University of Mashhad, and he was also a vice chancellor of Ferdowsi University of Mashhad. His expertise, he did his PhD from Cardiff University in 1995, and then he joined in the Ferdowsi University of Mashhad. His research interests are like this: growth sequence of groups, combinatorial group theory, probability group theory, Schur multiplier and isoclinism of groups, finite simple groups, graphs associated to groups and rings, and graph theory and combinatorics. He has produced more than 25 PhDs and many papers. He have more than 130 papers he have published in various reputed journals. We are very happy to have Professor Irfanian in our conference, and he will deliver a talk on some bipartite graphs associated to a group. Professor Irfanian, over to you.
Okay, thank you very much. It's my great pleasure to be here and see some of my friends in this talk. So first of all, I would like to thank the organizer of this conference and in particular my friend, Dr. Raja. And what I would like to mention here is to give some new bipartite algebraic graphs. You know, we have many algebraic graphs, but the number of bipartite algebraic graph is not so many. So I would like to introduce some of the bipartite graphs related to groups. So could you let me know how can I share my screen, please?
So in the bottom line, you will see present now. You will see a upside arrow. If you
Where?
in the bottom of your screen.
Yes.
So you will see, yeah, you will see a car. You will see an arrow which is upside. Yeah, you just put your cursor there.
The entire screen.
No,
Yeah.
you just
Yes, you can do it in that screen.
Yes.
you can select window also, and then you can present your. You can open first your PDF,
Yes.
then you select the window.
Can you see?
Yes, sir, it is. It is visible.
All right.
Yeah, you can make it full screen or whatever
So
you
go
wish.
to view.
Okay. It's better because I would like to move up or down, so
Okay,
it's
okay.
better to.
Okay, sir.
All right. As I mentioned, I'm going to introduce some bipartite graphs associated to a group. First of all, let me just give a classification. Of course, it's not a classification under AMS classification. It's the classification which actually we use for our department. You know, actually, if we look the mathematical sciences, you know, we have three main branches of mathematical sciences. We have pure mathematics, applied mathematics, and statistics, right? So if you look at sub branches of every of these three main branches, for example, in pure mathematics, we have algebra, we have analysis, geometry, topology, and so on. And in applied mathematics, we have numerical analysis, differential equations, dynamical system operation, research, control and optimization, graph theory, discrete mathematics, and so on. And in statistics, actually, we have description state, we have source and data, sampling concept, regression, data science, probability, and so on. So that's the three main branches of mathematical sciences. Just I want to give the motivation of my my subject in this talk. Right. In the first branch, if you take algebra, right, and if in the second branch you can take graph theory, and in the third branch you take the probability. So we have three sub branches: algebra, graph theory, and probability. That's from three main branches of mathematical sciences. And of course, in algebra, you know, we have many sub branches of algebra. We have group theory, we have ring theory, commutative algebra, non-commutative algebra, and so on, right? So what I would like to give here is to combination between group theory, graph theory, and probability. So what we can say about these three sub-branches of the main topics. If you combine algebra and graph theory, then we can get algebraic graphs. So we have many algebraic graphs. Algebraic graphs means the graph associated to an algebraic structure. For example, we have many graphs related to groups. We have many, like, for example, commuting graph, non-commuting graph, power graph, Cayley graph, and so on. And also, we have some more algebraic graphs related to a ring. For example, we have zero divisor graph, we have annihilating graph, and so on. We have many graphs related to rings. And also we may have some more other algebraic graphs related to a special algebraic structure like semi-group, semi-ring, vector space, modules, and so on. So that's the combination of algebra and graph theory is algebraic graphs. Now, if we take a group theory and graph theory, which is the just subject of my my talk here, is the graph associated to groups. We have many graphs associated to to groups. As I mentioned, we have committing graph, non-committing graph, power graph, and we have many graphs. But the point is that we don't have so many graphs related, so many graphs associated to groups to be bipartite. So most of graphs is not bipartite. So here I'm going to give some bipartite graphs to introduce some bipartite graphs associated to groups. And also, you know that if we combine the probability with the group theory, so we can get the probability group theory. Probability group theory means that we can define the probability. Just it means the special. You can take a special property of a group. For example, if you take the commutative property in a group, right? So we can define the probability of two randomly chosen elements, for example, X and Y, to commute. So this probability is called the commutativity degree. It means that we don't need to divide the commutativity for groups in terms of the groups is commutative or not. So if the group is if the group is not commutative, so we may have a different amounts of the probability. Sometimes the group is close to be abelian, or sometimes is very far. So we don't actually like to put all non-abelian groups, non-commuting groups in just one set. We can just give opinion of different types of the probability. So the combination of probability and group theory is the probability group theory. Now, the main subject of my talk is to give some probabilities in terms of the group, and also give some graphs. Of course, here I'm going to mention bipartite graphs associated to groups, and then combine these together. So combine the probability group theory and the bipartite graphs. This is just a little bit motivation of my talk. Now, I would like to give some bipartite graphs and some probabilities in this talk. So depending on my time, maybe I introduce 3 or 5 bipartite graphs associated to the groups. First of all, I would like to introduce one probability which is called normality degree, and then I will introduce non-normal graph. Okay, so let me give the definition of normality degree. Normality degree in terms of the probability, in terms of the probability, the property of a subgroup to be a normal subgroup. Suppose that G is a finite group. So if H is a subgroup of G, then we can define the normality degree of the subgroup H in G, which we can denote by this notation. That's the probability of H to be a normal subgroup in G. And we can define it by the following ratio. But the probability of a subgroup H to be a normal subgroup in G is the number of pairs H and G, which H is in H and G is in G. So we have a pair of 2 elements, H and G, such that we have this property G inverse HG is in H. You know, if we have this property for all elements G in G and for all H in H, then well, H would be a normal subgroup, and divide by the number of all pairs, which is order of H times order of G. So that's the probability, that's the normality degree of subgroup H in G. Okay, it's clear that if the probability is 1, then the subgroup H must be a normal subgroup. And conversely, if H is a normal, then the probability is 1, because if you look at this definition, if H is a normal, so it means that we have this property for all G in G and H in G. So it comes to all possible order pairs. So the probability is 1. So for this reason, I call this probability as the normality degree. Let me give just two easy examples. If you take the symmetric group S3 of order 6, we have 6 elements. We have identity 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. If you take H is a subgroup of order 2, you know that H is not normal. The normal subgroup of S3 must be of order 3. So we don't have normal subgroup of order 2. So H is not normal. Now, what's the normality degree of H? So what we have to do is to count all pairs. All pairs, as I mentioned, HG, which H is in H. So we have 2 cases for the first entry. So the first entry can be identity, and the 1, 2, the two cases for elements in H, and we have 6 elements in S3. So if you look at here, so identity, we have identity with all other elements in S3. So we have 6 cases for the first entry, the identity, and we have only 2 cases for the elements of H, because we have 1, 2, and identity. So it is 1, 2 to the identity is 1, 2, which belongs to H, and also 1, 2 to the 1, 2, which is the identity, and again is in H. So we have 8 pairs, and if we divide 8 by the order of H times order of S3, we have 8 over 2 times 6, which is 8 over 12, and it is 2 over 3. So the normality degree of H in S3 is 2 over 3. And we have the same computation. We can do it for the dihedral group of order 8. You know, we have 8 elements. And again, if we take a subgroup of order 2, the subgroup generated by element B, which is not normal subgroup, because the only normal subgroup of order 2 is the center of the dihedral group, which contains identity and A square. So H is not normal, and if we do the same computation for dihedral group of order 8 and subgroup H, we can get the normality degree is 3 over 4. So for any group and any subgroup, we can find the normality degree. Now, there are some basic results about the normality degree. For example, we can denote the normality degree in terms of the normalizer of an element G in H, right? So we will have the summation of the order of normalizer of any element G in H divided by order of H, order of G. And the second result is that if G is a finite group and H is a subgroup of G, and if P is the smallest prime number dividing the order of H, then we can get a lower bound and upper bound for the normality degree of H in G. This is the index of H, subgroup H in G, and that's the index of normalizer of H in G. The normalizer of H is the set of all elements G in G such that H to the G is H. And as I mentioned to you, we have the commutativity degree. It's very known, and there are many papers about the commutativity degree. So the commutativity degree of the finite group G is the set of pairs X and Y such that XY is equal to YX, so X and Y commute, divide by order of G squared. So I defined the relative commutativity degree for a subgroup H in G, and that's the number of pairs H and G such that H and G are commute, H is in H and G in G, divide by order of H, order of G. So it's interesting to compare the commutativity degree and the relative commutativity degree of H in G and the normality degree. So you can see that the commutativity degree is less than or equal to the relative commutativity degree, and that's less than or equal to the normality degree of H in G. Okay. Another result about the normality degree. So if G is a finite group, and if we have two subgroup H and K, which K is a normal subgroup of G and K is contained in H, then the normality degree of subgroup H in G is equal to the normality degree of quotient subgroup H over K in G over K. And also we can find an upper bound for the normality degree of a finite non-abelian simple group G. So if G is a finite non-abelian simple, then for any subgroup H, we have the normality degree of H in G is less than or equal to 8 over 15. And also, if we have two different groups, we have two groups G1 and G2, and we have two subgroups of H1 of G1 and H2 a subgroup of G2. So that's the normality degree of direct product of H1 and H2 as a subgroup of the direct product of G1 and G2, which is the product of the normality degree of both H1 in G1 and H2 in G2. Well, this is an interesting and easy exercise. If you take a non-normal subgroup of dihedral group of order 2 times n, then you can find the normality degree of H in G exactly by this formula. Now, let me introduce the first bipartite graph here, which is non-normal graph. So, suppose that G is, our definition about the bipartite graph can be defined for infinite group, but because I'm going to give a relation between these graphs and the probabilities, so I always assume that G is a finite group. But in definition, you may assume that G is infinite. It's not necessarily finite. So if G is a finite group and H is a subgroup of G, then we take two sets. Set A is H minus H sub G is the core of H in G. You know, the core of H in G is the intersection or conjugate of subgroup H. So that's the intersection of H to the G for all G in G. So the set A is H minus HG, and the set B is G minus the normalizer of H in G. And you know the definition of normalizer is the set of all elements G in G such that H to the G is H. Now, one more point is that, you know, we have H is always contained in the normalizer of H in G, and Hg, the core of H is in G, is contained in H, right? So this is very important to show that these two sets A and B are disjoint. So the non-normal graph of H in G, we can denote by this notation, right? With gamma Hg, we define this graph as a bipartite graph. So for defining the bipartite graph, we actually need two parts, two independent sets, right? So I assume that the vertex set for this graph is the union of A and B. And you know that A and B are disjoint. We don't have any intersection between A and B. It's very important if you want to define a bipartite graph. So two parts must be disjoint. Now, this is the vertex set. So if we have two vertices, if we have H in A and G in B, then we can say that H is adjacent to G if and only if we have H to the G is not in H. Let me just explain here. This is the graph, you know. So here is a part A. Part A is H minus HG, right? And here, the second part is G minus the normalizer of H in G. You know, if you take H is a subgroup of the normalizer of HG. So we don't have H in set B, right? But here is A is part of H. So we don't have any intersection between A and B, right? So we have an H between H in A and G in B if and only if we have this condition, H to the G is not in H. So that's a bipartite graph. Let me give just some examples. Again, we assume that S3 is the symmetric group of order 6 and take subgroup H as a group generated by transposition 1,2 is a subgroup of order 2. So we can easily see that the normalizer of H in S3 is the whole subgroup H. And if you take the core of H in S3, that's the intersection of all conjugate of H in S3 is the trivial subgroup. So how about the sets A and B? So A is H minus core of H in S3, which contains 1, 2, because we have to remove identity. You know, core of H in S3 is an identity, so we have to remove. So we have one vertex in set A, and here we have the normalizer contains 2 elements. So we have to remove 2 elements from the 6 elements of S3. So we will have 4 vertices in set B, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. So it's easy to see that the bipartite graph here is a complete bipartite, is a star graph is K1, 4. Another example is for dihedral group of order 8 and again subgroup H of order 2. So here you can find the normalizer of H in dihedral group of order 8 and also the core of H in the 8. And again, you will get 1 vertex in A and 4 vertices in set B, and well, we have again K1, 4. Now let me give some results. We don't have more time to explain the results because I would like to just introduce some bipartite graphs. So we cannot deal with the structure of the proofs. So if H is a normal subgroup of G, if H is a normal subgroup, then the core of H in G is H. And also we can see that the normalizer of H in G is the whole group G, because that's the equivalent just relation for the subgroup H to be normal. So what will happen? In this case, the set A is empty and also B is empty as well. So in this case, if H is a normal subgroup, so we don't have any vertex, not only in set A, but also in set B. So we don't have any vertex at all. So for this reason, we always assume that H is not a normal subgroup of G. But if H is normal, so we don't have any vertex, and trivially we don't have any H, so we don't actually need to talk about this graph. The second property is that, this is the set A. So the size of part A is less than of the set of part B. So the size of A is always less than the size of B. And here are some more results. So the graph has a pendant vertex if and only if the subgroup H has order 2 and the graph is a star graph. And if the size of H is bigger than 2, then the girth is 4. And generally, the diameter of this graph is at most 4. And the diameter is exactly 2 if and only if the graph is complete bipartite graph. And it's interesting to see that if the core of H in G is a maximal subgroup of H, then the graph is again complete bipartite by the size of H minus that's the size of A and size of B, right? And the independence number for this graph is the size of the biggest part, which is the second part. The size of B is the biggest part, so it's order of G minus the order of normalizer of H in G. And if H is a non-cyclic and we have this condition, then the graph is not planar. Now, I'm going to give a relation between normality degree and non-normal graph. So as you remember, I introduced the normality degree with this just relation. And here you can see that the number of pairs of H and G, we can divide in two sets. The set of all pairs, HG, which H to the G is in H, and all pairs which don't have this property, with H to the G is not in H. So we can see that the size of the first sets is the order of H times order of G times the normality degree of H in G, and the second part is the size of the second set is exactly the number of edges. So we can find this relation. This is the number of edges for this graph is order of H times order of G times 1 minus the normality degree of H in G. And here are two examples which we have already find the graph and the normality degree. You can see that the graph H subgroup H in DH, we have 4 edges, and if we put 4 in the above relation, we can get the normality degree 3 over 4. And similarly, for S3, we can also get the probability, the normality degree 2 over 3, and by having the number of edges and conversely. Now, the second bipartite graph is a special case of non-normal graph. You know, in non-normal graph, we assume that G is a finite group and we take a subgroup H. But if we have two subgroup H and K, such that H is contained in K, right? So we can define similar as the non-normal graph or normality degree. We can define the normality degree of H in K. It means that this is the generalization of the normality of H in G, because if we can define it for any subgroup K containing H. So if we take K is equal to G, then we can get the normality degree. So that's the relative normality degree of H in K. So we can define the relative non-normal graph of H in K, right? So we can put set A as the subgroup H minus the core of H in K. The set B is set K minus the normalizer of H in K. You know that if we put K is the whole group G, you will get the usual non-normal graph, right? So we may have some more results about this graph. The first one is that this graph is an induced subgraph of the just non-normal graph, and we have some more properties about the graph when the graph is completely bipartite, or when the graph is planar or is not planar, right? And also is for outer planar. Anyway, now I'm going to define the third bipartite graph. So the third bipartite graph, I just associated this graph with two sets, set of elements of G and set of cosets of subgroups of a finite group G. Let me define the graph. Assume that G is a finite graph. Now we can denote the L of G as the set of all subgroups of G. Now the bipartite graph we can denote by gamma G is a graph with two vertex sets A and B, the union of two sets A and B. We can put A is the whole group, right? And B is the set of all subgroups of G. Now, what we can say about H between any element of A and any element of B. So if we take X is an element in A, which is an element in G, and if we take H in B, which is H, is a subgroup of G. So we can say that X is adjacent to H if and only if the left coset of H and the right coset of H in terms of X are equal. So if we have XH is equal to HX. So as you can see, A is the set of all elements of G, and B is the set of all subgroups of G. And we have an H between X and H if and only if we have XH is equal to HX. So the left coset is equal to the right coset. Now, here are some examples. So if again look at S3, we have 6 subgroups. For S3, we have identity subgroup, we have 3 subgroups of order 2, 1 subgroup of order 3, and the whole subgroup is S3. So we have 6 subgroups, which is the in the second part we have 6 vertices, and also we have 6 we have also, let me just a little bit we have 6 vertices in the first part as a set of elements of G, and 6 vertices in the second part, which is the 6 subgroups of H of S3. So identity will adjust to all subgroups, right? And in the second part, if you look at H0, which is the identity, and if you look at H4, which is the subgroup of order T, it's a normal subgroup, and H5 is the whole subgroup. So these 3 subgroups will adjacent to all 6 elements in part A. Another example, if you look at cyclic group of order 8, then we will have 4 subgroups, and we have 8 elements. So this is the graph, and of course this is the complete bipartite graph. We have some results about this graph. So if the group G has at least 1 non-trivial and proper subgroup, then this graph has no isolated vertex. Isolated vertex means the vertex with the degree 0, so there is no edge meets this vertex. And the second result is that the graph is connected and the diameter is at most 4. And if the group has not trivial center, then, and also the second part has at least 2 elements, the Gertz is exactly 4. And you can see that the graph is complete bipartite if the group is the Dedekind group, means the all subgroups are normal. And we can also see that if G is a non-trivial group, then this graph cannot be 3, and the dominating number of this graph is exactly 2. And if G is a cyclic group of order prime number P, the graph is planar. But if G is a cyclic group of order P times Q for these 2 distinct 2 prime numbers P and Q, then the graph is not planar. And here also is another condition for the cyclic group of order N, right? If we have the composition of N in terms of the prime numbers, then the graph is planar, just in the case that the number of prime numbers is 1, so K is 1, and the power is 1, right? And also, if G is a finite group, then we can this classification for the planarity. If G is not simple, and then the graph is not planar, and if the graph G is simple, the group G is simple and abelian, then the graph is planar. And if G is simple and non-abelian, then the the graph is not planar. It's interesting to see the structure of the graph for dihedral group, some different types of dihedral group, and check the Hamiltonian properties. So the this graph for dihedral group of order 2 times p is Hamiltonian if and only if p is 3. So it means that for dihedral group of order 6 is also the graph is planar. And if p is the prime number at least 4, and if n is p square or p cube, and then the graph for dihedral group of order 2 times n is not planar. And we can say the similar thing for dihedral group of order 2 times p to the k. It's not Hamiltonian, and this is the conjecture which I left this for anyone who are interested to deal with this graph. So I conjectured this graph, the bipartite graph which I defined for dihedral group of order 2 times n is Hamiltonian if and only if n is 3, right? And here are some research problems. So we can check the Hamiltonian property for some other kinds of groups, for example, for the generalized quaternion group, for semi-dihedral group, for projective special linear groups, and so on. And also we can just find the adjacency matrix. We can find the eigenvalues of the adjacency matrix and the energy of this graph for some kinds of groups. Okay, the last bipartite graph, which is the fourth one, in the next 6 minutes, I'm going to just introduce this graph very quickly. Again, I define a graph, a bipartite graph for a given finite group G and subgroup H in G. So the bipartite graph for subgroup H and in G, so we can again define 2 sets A and B. Look at sets A and B. So we can put A as the set of all pairs H. Both integers are equal for H in H, and B is the group G. Now we can say that if we take the pair H and H in set A and element X in G, then we can say that the pair H, H and X are adjacent if we have the commutator of X, H, and H is not identity. You know the definition of commutator of X, H is X inverse, H inverse, X, H. And the commutator for 3 elements, X, H, H, is the commutator of the first entry is the commutator of X, H, and again, this commutator of this commutator with H, right? So if you look at S3, you can see that we have 6 vertices in the second part and 2 vertices in the first part. And you can see that we have H between the pair 1 to 4 of them. So we have 1 isolated vertex in set A and 2 isolated vertices in set B. Now, when we want to define a bipartite graph or any graph, so we are interested to have no isolated vertex. So if we want to remove this first the 1 vertex from set A and 2 vertices from set B, so we have to just have a restriction for sets A and B. So I define the set A and B we put the set A as the pairs H for H, the pairs H and H, for any H in H, minus this set. This set means the set of all pairs H, comma H, which we have the commutator X, H. H is identity for all X in G. So we remove this set, and also we remove the set of all elements G in G, such that the commutator of G, H is identity for all H in H. By this restriction on sets A and B, then we can see that we don't have any isolated vertex. So the previous graph can be deduced to this graph, which is the complete bipartite graph, is K14, this star graph, right? Now, here is another example, right, for the alternating group and the subgroup H of order 3, right? And here are some results. So you can, as I mentioned, the new graph, the new sets A and B, this is the result for the new graph. So this graph has no isolated vertex, and if H is a normal abelian subgroup, then we will have set A and B is empty, so the graph is a null graph. And if G is a non-abelian finite group and H is an abelian subgroup, then we can see that the graph is a star graph in and only if the first set, the set A, has only one vertex, and the graph is not Hamiltonian. The graph is Eulerian if the size of A and B are even. And here is the structure for this graph for dihedral group of order 2 times n, and subgroup H is a subgroup of order 2 for odd n, right? And just at the end, we can define a 2-angle degree. So for any group G, we can define 2-angle degree with the set of all pairs X and Y, which we have this condition, the commutator Y, X, and X is identity. You know, 1 angle is the group is exactly the commutativity degree. This is the 2-angle degree. Divide by order of G squared, and we can define the relative 2-angle degree for any subgroup H in G. So the set of all pairs H and G such that we have this condition. So it's interesting to see that we have the relation between the number of edges of this graph with the relative 2-angle degree. So the number of edges is the order of H times order of G times 1 minus the 2-angle degree, relative 2-angle degree of H in G. So we may set some more questions, some more problems. You know, that's the beginning of introducing this graph. So if you are interested to do something on this graph, so you can do by yourself, or you can just keep in touch with me to do something more about these graphs. You know, we have many work on these graphs. We can do something about spectral graph theory, about many things, some kinds of coloring, and many problems in group in graph theory. Okay, so I should stop because my time is finished. So if you have any question, I'm ready to state it.
Thank Thank you, Professor Irfanian, for your nice talk.
All right.
Let me ask some participants if they have some questions.
May I ask a question?
Yes, sir, please.
Of course, yes.
Professor Irfanian, you gave an excellent talk. Thank you for this. Very nice exposition. And actually, I have been interested in probabilistic group theory. I did some small things with Rajat long back. Not so
Yes.
long, but yeah. So this normality degree.
Yes.
It's clear that when its degree is 1, then of course the subgroup is normal. Are there some bounds, like if the normality degree is this much or more than that, then the subgroup is always normal?
Yes, there is. You can keep in touch. There is a paper about this, and we have a lower bound and upper bound for the normality degree. Yes.
Okay. May I ask one more?
Okay. Yes, of course.
Okay. So whatever you have defined for normal subgroups, perhaps for the normality degree for a subgroup, you can also define it normality degree for a subset. Because
Yes.
there is also a concept of a normal subset.
Yes, this is exactly what I wanted to suggest at the end, because if you take a subset in terms of the subgroups,
Yeah.
so you will lose some more properties of the subgroup. But even you have definition of the normal subsets. So it means that this is the generalization of my definition, because you consider the subset, not subgroups. So in the special case where the subset is a subgroup, that's a very good idea to this, yes. Of course, it's a little bit difficult, because if you take a subgroup, so you don't have any more properties. So the multiplication of 2 elements is not necessary to be inside of set.
So
You may lose something, but actually you may give some general properties for this graph, which this property actually includes the non-normal graph. So if you prove something here, so it means that if you take X as a subgroup, so actually this property is